Hello, everyone, and welcome to day 3 of Geography 2050, the future of the world ocean. It's Hump Day, or as I like to call it, Humpback Day. I'm sorry, that was terrible. But you know what's not terrible? Today's schedule. Today we're going to be talking about exploring, mapping, and sensing the ocean. Before we get into our panelists and our talks, I'd like to remind you to check out the rest of the website. As a reminder, there are daily quizzes. And there is the vault where you can access all material from today and previous days of the conference anytime in the future to share with your friends and colleagues. I'd also like to take a second to thank our longtime partners who help us put this event together. And the Geography 2050 event's been going on for a number of years, and we hope to continue it in the future, and we absolutely could not do it without you. So thank you very much. Another thank you, I'd like to thank our premium sponsors, which you can see here on the screen, as well as all of the rest of our sponsors. Without you, we would not be able to put this event on. And again, we really appreciate it. And thank you very much for all of your support. The last shout out I'd like to give is if you navigate around the website, in addition to the vault and the quizzes and all of the material from this week, you'll also find a tab where you can donate to help support this event and ones like it in the future. So please feel free to explore that option. Moving on to today's topic, I'd like to discuss ocean mapping and, exploring, mapping, and sensing the ocean. We're going to start off with a very exciting panel with some of my heroes, including Dr. Bob Ballard, Dr. Sylvia Earle, Dr. Catherine Sullivan, and Dr. Don Walsh. We'll be moving from there into spotlight sessions, including one scientist who I greatly respect and admire and has been a mentor to me in my career, Dr. Larry Mayer, who's a exceptional oceanographer and hydrographer at the University of New Hampshire. We'll be moving from there to 5 different lightning talks on a wide range of subjects related to exploring and mapping the oceans, and concluding with a book review and an interview with Mr. Christian Harder and Dr. Don Wright, 2 friends and collaborators of mine as well, talking about their book, GIS for Science, Applying Mapping and Spatial Analytics, the 2nd volume. So without further ado, I'd like to move to our first panel, the Ocean Explorers. Welcome, everyone, to our Exploring, Mapping, and Sensing Our Ocean section of Geography 2050. My name is Christopher Linden, and I'm the CTO of a little company called Applied Ocean Sciences. And before that, I was a Coast Guard officer. Today, we're going to be talking about ocean exploration with some of the world's greatest explorers, and I couldn't be more excited to be here. I'd like to take a minute before we get started with our explorers to discuss why this is such an interesting and exciting topic to me. This picture right here is one that you might be familiar with. This is the world, as many of you are used to seeing it. The world as I'm used to seeing it looks more like this. This is just from a little bit of a different angle, centered on the Pacific Ocean. And you can see that we live on a big blue marble. The world is over 70% covered by ocean. And exploring that ocean is a challenge. What makes it difficult to explore is that human beings don't breathe so well underwater, and the crushing pressure at depths can make enormous engineering challenges for exploring and sensing the ocean. Beyond that, the ocean is 4-dimensional. We have a volumetric body of water that has properties at every X, Y, and Z coordinate, and those properties change over time. So even if you sense someplace one time, it will change in the future. Additionally, we typically interact with our world through RF or electromagnetic radiation, either through optics with our eyes or sensors like LiDAR, radar, things of that nature, infrared sensors, multispectral. And most of these bands that we use for sensing in air and throughout most of the world don't penetrate very well underwater, which also makes the remote sensing of ocean depths very, very challenging. And what's more, it's expensive to get heavy marine equipment to the ocean depths, take tens of thousands of dollars per day in ship costs and related expenditures. So the ocean is big, it's volumetric, it's changing, it's opaque to our eyes and our sensors, and it's very, very difficult from an engineering perspective and expensive to explore. So that is why panelists like the explorers we'll be talking to today have devoted their lives to solving many of these problems and exploring the ocean depths despite all of these challenges. So I'd like to take a minute to introduce our panelists today. In no particular order, Dr. Don Walsh is a Naval Academy graduate from 1954 and retired at the rank of captain. He has a PhD in physical oceanography from Texas A&M and more awards than I could possibly name today. He was named one of the world's great explorers by Life magazine. He's dove on the Titanic and the Bismarck, and he currently holds a professor position in the College of Earth, Ocean and Atmospheric Sciences at Oregon State. Our next explorer is Dr. Catherine Sullivan. She is the first American woman to have walked in space and to have dove to the bottom of the Marianas Trench, and the only person to my knowledge who's done both. In addition to her many achievements in ocean exploration, she served as an administrator for NOAA and an undersecretary of Commerce for Oceans and Atmosphere, and is currently a senior fellow at the Potomac Institute. Next is Dr. Bob Ballard. He is the president of the Ocean Exploration Trust, the director of the Center of Ocean Exploration at the Graduate School of Oceanography at URI. He is well known for the discovery of the RMS Titanic, as well as dozens of other notable wrecks and other marine archaeological discoveries. He was the first to film deep sea vents, and in addition to these notable scientific and exploration achievements, has done incredible work in scientific communication and popularizing the sometimes otherwise opaque world of ocean exploration to future generations of ocean explorers. Finally, Dr. Sylvia Earle is the president and chairman of Mission Blue, National Geographic Explorer and Resident, founder of Deep Ocean Exploration and Research, Inc., and with Mission Blue has created over 50 hope spots worldwide to protect delicate ocean ecosystems all over the world. I am absolutely honored to be speaking with all of you today. And it's an absolute privilege to chair this session. Thank you so much for your time. The format for today's session is open-ended. I'll start with a couple of questions and we'll see where the conversation takes us. I'd like to start with the question that I introduced briefly in the introduction, and that is that with 70% of our ocean surface covered by water, it has been said by some that by some measures only 5% of the ocean has been explored. And a common quote that you hear in pop culture is that we know more about the surface of the moon than the seafloor. My first question is that true? And if so, to what extent is it true? And I'm going to go in the order I see on my screen there. So maybe we can start with Dr. Sullivan.
Sure. Thank you, Chris. It's great to be with you. I think there's a huge degree of truth in that metric. One can quibble on several dimensions, but let me just highlight one. Certainly from a topographic or bathymetric point of view, because of the factor that you cited, the opacity of the ocean to the wavelengths that we usually use for precision mapping, LiDAR in particular, we certainly do have, I think the number I know is about 400 times better resolution on the surface topography, not only of the moon, but of Mars, than we have on the bathymetry of the deep ocean seafloor.
Wow. Dr. Earle, you're next in the order on my screen. What are your thoughts?
Well, I'm still trying to get my mind around the combination of Dirk Pitt and Bob Ballard. You had a dream of being some combination thereof. But back to your question, what makes the ocean, what makes Earth really special in the universe, as far as we know, is life. And most of it is in the ocean. And I really suspect there is life of some sort elsewhere, but nothing like what we have here. And it's the ocean, where life surely originated on Earth. And it's where the greatest diversity and abundance of life really is. And we have literally just scratched the surface, just beginning to wrap our minds around not just the diversity and abundance, but we're beginning to recognize that all of the ocean is alive, that Earth is a biogeochemical miracle, and you can't pull them apart. I mean, you can look at the geology, you can look at the chemistry, you can look at the life, but you can't really understand any of those things unless you look at it as a integrated system. And is it more complicated? Yes. Do we know less about it than the moon or Mars or other parts of the cosmos? I think that's probably fair to say. At least we're beginning to understand the magnitude of what we don't know. And that's a great place to start.
Your point is very interesting. And, we talked about just mapping the seafloor and what percentage of that we've done, but the ocean's more than a seafloor. It's, the
Right.
physical oceanography, the chemistry, and the biology. And it's amazing to me that we're still discovering, new species, and not in, the small, phytoplankton only, but macrofauna, that we're still discovering every year.
I think even more exciting is the micro, the discussions that rage on about, are viruses alive, or are they just somewhere between the bio and the physical and the chemical? I mean, and that the ocean is where the action is with respect to viruses. And thank goodness they're there. If they didn't exist, we wouldn't exist. They're really critical to the chemistry of the planet. And we're just beginning to lift the lid on the big questions about what viruses are. And occasionally one of them likes to choose us as a host and gets our attention, but the great majority are out there, down there, doing their wondrous things in terms of shaping the way the world works. And maybe it's a separate kingdom. We're the ones who like to put labels and numbers and categories of things. Viruses don't care. They're just whatever it is they are on all the rest of the microbial world. I mean, Ballard, you were there. The discovery of the archaea, for heaven's sakes. When I was a kid, that whole kingdom of life was not known to exist. Now we know it exists even in our own bodies. Huh. So
that's an excellent transition, Dr. Earl. So I was looking at some of the Nautilus live footage last night online, and I saw several times in which, species that had not yet been identified showed up there for the first time for the general public to see. And that got me excited, and I bet everybody else who watched it as well. And Dr. Earl also mentioned, some of the new species, and many of those species are in the hydrothermal vents that I also saw footage that you collected, Dr. Ballard. What are your thoughts on that? The statistic of only 5% being explored, and how much we know about the ocean versus how much we should know?
Well, I'm an earth scientist, and I've been looking at the planet as a total system, dominantly covered by water. But I've done 157 expeditions at sea and probably zillions on land. I don't separate the water from the land. It's the system. And as picking up where Sylvia is I'm a believer in the concept of Gaia, that the earth itself is a creature, and that it lives in a symbiotic, hopefully a symbiotic relationship with life on the planet, certainly with most of the planet. But the human race is now becoming a threat to all of the above, a threat to the planet, a threat to all its life. And I think the earth is fighting back. I think we need to really think about what's going on right now. The earth, I think, has now recognized our presence and sees it as a threat. And I think the deal we've got to be able to cut a deal with this planet so that we're living in a symbiotic relationship with it. So understanding the whole system, but certainly a big part of that whole system, as Sylvia pointed out, the largest living space on the planet is the midwater zone, which is probably the least explored in the oceans. Yes, we're doing a really good job now on exploring the bottom of the ocean, but we really need to look at the whole enchilada. And this whole new program, the program that Woods Hole has with the Mesobot, we're looking and tracing and following creatures That is so exciting. I think we're at a critical moment in the history of the human race, because we've got to save this, not only the planet. I'm not really worried about Earth being here in 1 billion years. I'm worried about us being here in a couple hundred years. And so we really need to understand this planet more than we've ever understood it before, and time is running out.
We need to make peace with the planet.
Absolutely.
Yeah.
And I'd like to pick up on a comment you made about an enormous part of that Earth atmosphere, land, sea system that we need to understand better in order to understand those the challenges that we're facing is the ocean. And doing a little bit of background research for this panel, I couldn't help but stumble on Dr. Don Walsh's name a few dozen times when it came to exploring the deep parts of the ocean. So I'd like to hear, Don, your thoughts on that first question before discussing some of those challenges that Dr. Ballard just mentioned about the ocean, what percentage of it's been explored, and why, what challenges there have been to exploring the ocean.
Well, I think one of the things that concerns me a bit is we've been pretty easy, pretty loose with saying that only 5%'s been explored, 10%, 15%. Last number I saw from NOAA, and maybe Kathy can correct me on this, was 85% unknown. Still, that's, call me a liar for 10%. That's a big unknown, big question mark. The thing that concerns me, and I think we in the ocean community have to be very careful on this, is we don't really define that term exploration with respect to how much is known and unknown. And we have a rough topographic idea of the shape and form of the world ocean seafloor. We don't have a lot of detail, but how do we define in this context exploration? I just hate to see us get caught out by being accused of kind of using a rubber ruler to make these kinds of statements. I've never seen anybody question that before, so I guess I'm a lone voice. But I think with such a critical thing, exploration of the whole world ocean, we need to be careful what we mean by how much has been explored, how much has not been explored. There is a program underway now with the International Hydrographic Office in Monaco to map the entire floor of the world ocean by, what is it, 2030? I don't have that in front of me.
2030.
But
Yeah.
2030, okay. And that's a very ambitious program. And when they say that, now we get into the question that Kathy kind of implied, and that is resolution. That's the big thing. What is the resolution? Now, moving off of that for a minute, I'm just leaving that as an open concern of mine. I've had the good fortune to be on 3 expeditions to the Challenger Deep. One that I did 6 decades ago, and then with Jim Cameron in March 2012, and then 2019, last year, with Victor Vescovo and his 7 Deeps expedition. And it's just amazing to see the arc of technology and what's doable, what's possible now. In fact, between Jim's expedition in 2012 and Victor in 2019, it's astounding. The submersible system that he has was able to make 4 dives at Challenger Deep in 8 days, and Victor piloted 2 of those. And then this year, in his Ring of Fire expedition, which is sort of ongoing now, they've had some technical problems, but I think they're going to resume early next year. They've done a lot more. In fact, Victor, I think, has made 8 or 10 dives to Challenger Deep. Think of that. I know how hard it was in my time. We had considered a second dive, but we just couldn't manage the logistics. And Jim, for a variety of factors, wasn't able to do more than 1 dive. So we're beginning to scratch around in these deepest reaches of the ocean. And it seemed to me, Jim made his dive a half century after I made mine. And I take no pride in the fact that I have an alleged record and blah, 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 all that stuff, because I would have been really happy, elated, if somebody had been out there 2 weeks after we had been, Jacques Picard and I had been there and was doing it. It means we just left that small corner of the world ocean untouched. And yet, if we're to understand how our large part of our planet works, we know a lot about where seafloor is being created in the spreading centers. We know very little, although it's getting better now, about where it all goes. The other end of this is like a giant conveyor belt. We got the source. We don't have much information on the disposition, where the stuff goes, and trying to understand some of these fundamental Earth processes. Now we're getting at it. And people say, well, look, only 2% of the world ocean floor is the deep trenches. And if you can build a submersible, manned or unmanned observation system that can go to 6,000 meters, roughly 20,000 feet, then you can look at 98% of the seafloor. So as a bean counter, what a deal. I mean, for a capability, something less than, a little more than half the full depth of the ocean, world ocean, you can get 98% viewing area, if you will. But that begs the question of the deep trenches, that last 2%. And I know Sylvia's pointed this out for years, that that's like saying you can't go to the top of 2% of the mountain. I'm extrapolating your words from long ago, Sylvia. The general idea is, why would you forbid not full access to everywhere? Well, now we're doing it. We're doing a very efficient system. And I know Kathy is more recent on this. I am. It's last June, was it, or May?
Yeah, June.
Go there with it. And so you've seen the whole system. It's an amazing thing. Now,
but the point,
your heart is only about 2% of your body too.
Yeah, there you go. Very well put. So the point here is the world now has a system that allows scientists to go to any part of the ocean floor, a complete system. And I think that's an important notion, system. You just can't have a submersible ab initio like we did with the Triaster Jim had with his sub. You have to have a complete system, the mothership, the landers, all the instrumentation, and a wonderful seafloor mapping system that they have on board that ship, which does hydrographic quality output, stuff that can go almost right on to the charts of the seafloor. And they did two, in the five deeps expedition last year, 2019, they did something like 250,000 square miles of seafloor, most of which had not been mapped before. So it's an amazing system. And I guess you guess from my comments, I'm pretty much a supporter and enthusiastic about it. At this point, I'll sign off because I'm sure that Kathy can give us an update.
Actually, what I want to, Chris, what I would like to pick up on, sort of drawing a string through Sylvia and Bob and keying off of Don's worlds. It's great to talk about how much has been explored, and that is kind of an acreage or a yardage sort of discussion, if you want. But what I think about is the other word we've used here is how much do we know? And that's really where I key in, because to me, I'm on this point of living wisely and well on this planet. How do we do a better job of living wisely and well on this planet? That's not just about where have you been, or where did you peak at, or where did you make a measurement. That's about what you actually know, what depth of understanding of the processes and of the interactions between these systems. Sylvia's put her exactly right when she says it's an integrated system of systems that's physical, chemical, biological, and atmospheric, by the way, because the atmosphere interacts with the ocean and vice versa. And so when I think about what is the big challenges and the big opportunities in going forward with both ocean exploration and, more importantly, actionable, valuable ocean knowledge, I think of two things. Bob put his finger on one of it, the mesopelagic, this massive segment of the ocean that's full of life and a vital tranche of both the ocean food chain and of our life support system. But then my technical brain kicks in, because the other challenge I think oceanographers need to overcome is fundamentally a geographic and a technical challenge. It is too much the case today that each expedition, when it goes out, whether that's a single university lab or Caladan or NOAA, there's still much. I'm going to be deliberately a bit brash and unkind here. It is all still rather too much artisanal. It's a new instrument. It's a particular data system. It's a certain format. And so you get lots of little dots of insight, but they cannot be collected and aggregated. They don't become tiles in a unified mosaic. But metaphorically, we need to API the ocean. We need, or as with my NOAA hat on, oceanographers need to start acting more like the World Meteorological Organization, that there is some coherence and some unity and some standards about how we report and measure and record anything we have observed, so that the next group along can put the pieces together and not just look at my paper or Bob's or Sylvia's, but start to see the greater mosaic in area, in depth, and most importantly, in the living web that suffuses the entire world's ocean. How do we get to that point where our knowledge can become 1 + 1 is not 2, 1 + 1 is a half now. How do we get in the direction of 1 + 1 is 3?
If I could jump in, I think that we're right at the edge of the first time when it's possible to realize that vision. Esri, the organization that does GIS mapping and integrating information, turning their attention in recent times to the ocean. What we're doing with Mission Blue, with our now network of 133 so-called hope spots, they're not fully protected, but engaging communities, scientists, individuals to use the Esri format of story maps of a common framework that taps into the same kind of technology that NOAA uses, that NASA uses, that universities around the world use. I mean, whatever it takes, you're absolutely right, to be able to gather information with a format that is shareable, and consistent, and to be able to really look at change over time.
And measurement standards. I mean, key factor in why we all enjoy a decently worthwhile weather forecast is because all of the countries on the planet, more than a century ago, agreed whatever they wanted to study and measure, they agreed to consistently, regularly make a certain set of measurements according to certain standards with certain precisions, and then certain reporting formats. And it's actually a very thin layer of standards and data underneath all of the abundance of atmospheric research. But it is a powerful, it's like the connective tissue of your body. It's what makes the integration and synthesis possible. It's what makes it possible for us to represent and model the entire globe atmospherically and make forecasts that can actually help shape decisions that we face in our daily life. Let's get to that in the ocean, and in particular with respect to the living systems.
And coupled with that, I'm going to poke Bob Ballard just a little bit because
she loves to poke me. She's my wife's cousin, so she really likes to poke me.
It is a great sport, Bob.
Poke away.
And also to send you a big bouquet, because in the time of the pandemic that we're now experiencing and what we're doing right now, face to face, but we're not together, it's the virtual appearance that has come a very long way in the last 50 years. Used to be the telephone and party lines and all of that, but now we have the capacity to vicariously visit. Well, I have seen what you've seen, Kathy, because you brought back images and your personal experience you shared with me and the world. I don't imagine, I mean, I've been up 11 kilometers in the sky, as deep as you and Bob on, and now a handful of others have been deep in the sea. In fact, gazillions of people have been 11 kilometers in the sky, but I haven't been far enough up in the sky to really grasp Earth as you have seen it, but you have shared your view. And I think that's transforming everything. The ability not only to send our instruments, to send the cameras, but to send our telepresence, to use Bob's language, but also to take real live individuals. It was not just a camera up in space, it was you, Kathy.
Well, and Bob's done that at sea, not just sending pictures home, but taking us with him out to sea. And I think that's a huge, perched on your shoulder, Bob, feeling like kids or usins are with you. That enriches the experience for everyone who's taking part.
I'd love to talk about that a little bit more. I mean, I looked at the sailing log for some of the recent Nautilus trips, and I see brilliant scientists, incredible engineers, and then media people and graphics people, and people who specialize in content. And that can't be easy. What made you prioritize, the ability to share and communicate what you're doing?
A real simple story. When I was a little kid, I wrote a letter. I wrote a letter to Scripps saying, I want to be an oceanographer, and I'm dyslexic, so I'm sure I misspelled it. And they were kind enough to answer my letter. And not only did they answer my letter, they let me go on my first expedition in 1959 when I was 17 years old.
Wow.
And I fell in love with it. So think about the letter I wrote that normally ends up in a trash can. Someone answered it. So I come back from the Titanic in the first week, 16,000 Bob Ballard letters came to me. And I had a moral obligation. I could not say no. And that's why I created the Jason Project, to be able to take all these kids with me. And yes, I love the experience of being there physically, but I also, I had a big, long discussion with Jim Cameron just the other day. When I watched Avatar and I watched the guy leave his body and go into a Na'vi, he basically moved his spirit. And that's what I'm really into. I look at my hands as an amazing robot, but I separate my spirit from my physical body, and I want to beam people. I want to take their spirit, because I can take them by the tens to hundreds of millions, something we just can't do with a lot of physical bodies. And that's why right now with our expedition, we take millions and millions of kids, because they can literally beam them down Scotty. And so I love it all. I love physically doing it, but I also know that my spirit is indestructible and can move at the speed of light. And particularly as I get a little older in age, I rely upon my spirit a lot more than I have my tongue.
But Bob, it's not either or.
It's both.
It has to be both.
Yeah.
If we took cameras up in the sky, it wouldn't be the same as having Kathy up in the sky.
And it's appalling how many kids in America can't swim. If you can't swim, you're terrorized about the ocean. We need to make sure that every child on the planet, but certainly in our own country, particularly people of color, 90-some% don't know how to swim. It's
No
hard
child.
to say they're terrified.
No child left dry.
No child left dry. I love that.
In the water, and everyone knows how to swim, but I also know I'm a land-breathing animal.
Yeah.
5% of the human race, 95% of the human race live on less than 5% of Earth. There's a reason.
We always underestimate the value of communicating, but if you think about all the challenges, Bob, that you mentioned at the beginning of this, the challenges that Sylvia is working on in her Hope Spots, to me, one of the biggest challenges to overcome is that these problems seem less accessible to people. Like, we're used to seeing something on land. We're used to seeing a deer or an animal that we've seen in with our own eyes. We can understand conservation challenges that are related to that deer, that animal that we understand on a personal level. But the ocean seems so far away. I mean, not opaque just to our sensors, but to our imagination. And so what you've done with communicating, the ocean, I mean, and for lack of better words, making oceanography cool, making it accessible to so many people is so important.
I think one of the big breakthroughs happening right about now is to recognize that there are communities of other beings on the planet that we can relate to. Not that that should be all important, but it is, because we are a dominant force in changing the planet right now. But it's come over the past few decades, understanding, for example, the societies of whales and the communication that they have, the family structure, and it comes from really getting to know individuals and their relationship over decades, to know not only how long they live, but what kind of relationship do they have with their families, whether they're the orcas up in Puget Sound or the sperm whales that have been tracked down in Dominica over a period of now 20 years. And to know I mean, it's really a human thing, but to give them names. Jane Goodall got a lot of flack from the scientific community because she gave chimpanzees names. You can't do that. That's anthropomorphizing the animals and personalizing them, and you have to be detached. Well, that's nonsense, she said, and I say too. Getting to know how these creatures live, and then to be a tuna fish, if you could just imagine what it takes to get from one tiny little speck into a full-grown 1,000-pound giant. Again, it's a miracle that any of them survive. And then until we came along, their biggest threat, probably orcas and sometimes big sharks would eat a tuna. But when they're grown up, when they're small, they get eaten by everybody. Just tuna lunch for. But the thing is that if we can get to know them, to empathize with who they are, not just what they are, and there needs to be I think, an ethical transformation about the way we treat other forms of life on the planet. On the land, we've come a long way. We have policies protecting birds. Yes, we still have a long way to go to protect and respect other forms of life on the land. But in the ocean, people say fish and they think, delicious. Lemon slices, butter, fried, baked, rather than thinking of life in the ocean as something to be treated with dignity and respect, and not just to think of them first and foremost as commodities. We used to think of whales first and foremost as commodities. We've sort of evolved with a different relationship, and those of us who are here gathered right now, we're witnesses to the transformation in the ethics of how we treat our fellow mammals in the sea.
Dr. Earle, I'd love to dive deeper into that, because the part of it was motivated by what we were talking about before, which is how distant many people in the world feel from the ocean, just by pure proximity, or by the fact that people don't interact with the ocean and they're scared of it. They can't swim, whatever it is. The ocean's hard to get to, and there's that distance. And that's the kind of thing that the scientific communication that Dr. Ballard's been working on is so important for. But another part of the two challenges that you just mentioned, which is, with the marine mammals and how, we used to think of whales as a commodity. We still think of tuna as a commodity. Brings up another issue that I'd like to mention, which is that the ocean in a lot of ways can be considered almost the ultimate tragedy of the commons, and that anything that any of us do to the ocean affects the entire ocean. Tuna, for example, are highly migratory. If we catch all the tuna in our waters, they don't get into someone else's waters, which means solving a lot of ocean problems requires levels of international cooperation, which are enormous and often challenging. And I'd like to ask Dr. Walsh briefly about that, because as I understand, he was on the Law of the Sea Advisory Committee for the Department of State. And that is, I think, from an international cooperation perspective, a triumph in what you guys were able to accomplish. Could you comment a little bit, Dr. Walsh, on the international nature of some of these issues and some of the challenges that pose?
Sure. First of all, I think the Law of the Sea Treaty was a remarkable enterprise when you could get all of the nations of the world to agree on a somewhat uniform legal framework for the world ocean. And
Do you think you could describe the law of the sea very briefly for our viewers who might not be as familiar with it?
Oh, gee.
Try to put you on the spot like that. The 30-second version.
Having sat through some sessions in New York at the UN, I've seen geological formations that move faster than that lot. But there were 3 Law of the Sea conferences. The first one was 1928, and really didn't do much, but it was the beginning. And then in the 1960s, there was a second one which defined the outer continental shelf, which was very important because it gave to the coastal states certain rights to the adjacent coastal waters out to about 200 miles. And then the third conference more or less institutionalized all of that and added many other things. I was on the Committee 3, which is Freedom of Scientific Research, because once you have given a coastal state rights, but not sovereignty, rights to a 200-mile wide swath off their shoreline, then that implies a certain agreement that they had regulatory functions. So if you come in there with a scientific research ship and start working there, then that's considered to be working in their area. If you're not doing anything, and that's called innocent passage, then that's fine. Every nation has the right to send their ships through the 200-mile exclusive economic zone because you are innocent passage. You can't stop and do things, fire off missiles or do science and so on. So this all of a sudden gave all the coastal states in the world the ability to put a hand into the pot with respect to scientific research. The nations were not supposed to deny access for scientific research unless there was a very valid reason, but they also were given the right to participate in such an expedition. Well, you can imagine from the country of Togo on the coast of Africa, of West Africa, a little difficult to round up enough oceanographers to go to see a script ship or a Woods Hole ship, but that's their right. And they also have, that government has the right to the scientific data that might flow from work carried on in their waters. But I think what's really amazing, the fundamental thing, is that how you could get 165 nations, I think it was the time that the treaty was finally signed, not ratified, but signed by the signatory states around 1991, something like that. And still could agree, because so many of them, and especially certain nations, think they have their hands on the levers and their feet on the pedals. And it's really hard to get everybody to agree to things. And yet it happened. And when it started out, by the way, the third UN Law of the Sea Conference, there were 65 nations. I mean, you could almost invite them to dinner and hammer it out over a pastrami sandwich. But by the time you had 165 nations, I think the count's up to 180 now, something like that. And yet it worked. I think it's just amazing that you could get the international community to agree on anything. So it's a good paradigm for a lot of other activities we're trying to do internationally, whether it's, climate change accords, things of that sort. And why was I involved? I was a naval officer. I wasn't a lawyer. I didn't have any background in maritime law or international law. But my feeling by imposing myself on these lawyers was simply that it's too important to leave to them alone, because I, as an ocean person, and everybody else on our panel here, have to live with the consequences of what these people did in New York, the Law of the Sea Conference. So I got involved that way, just to kind of make sure I understand what they were doing and perhaps give the blue flavor to the discussions. This could be a 3-unit course in university, the history and execution of the Law of the Sea. So,
do you mind talking a little bit about the challenges associated with the IOC and data standards?
IODC.
IODC, excuse me.
Well,
Thank you very much, Dr. Earl.
I would rather push that over to Kathy, because she was responsible for a lot of that stuff during her as chief scientist of NOAA and later as administrator of NOAA. So yeah, Kathy's more up to date than I am. And of course, Sylvia was asked the question and I jumped on top of it. So I'll stand back for a moment, please.
Well, let me take a stab at it without droning on too long. There have been efforts in the past to try to forge a single repository, a unified repository for oceanographic data. And the one that comes to mind is the IODC, the International Oceanographic Data Center, back when. Don can tell me, I think in the 60s sometime. But the problem was the IODC was basically a big bucket that welcomed anyone to pour whatever they had into it. And that's nice. But if you think in comparison to, say, the World Meteorological Organization, what you're trying to do is bring together data, measurements, observations in a way that lets them really be additive and really scale up to a deeper understanding, deeper insight, and prognostic and forecasting capabilities. And if you want to move in that direction, you not only need a bucket, but you need very clear agreements that are peer enforced about what is the essential set of measurements everyone will commit to make. You can make whatever other ones beyond that you wish, but we all agree we'll do these X number of measurements. And then you need, even more importantly, you need agreement about standards and calibration. So I need to be able to know that when Bob measured the concentration of something in an aliquot of seawater, I know that's an accurate, precise measurement, and it compares to mine in a certain way. I can count on that. I've got quantitative rigor to it. That's what has not happened yet in the ocean world. To the best of my knowledge, and I welcome my colleagues to teach me and correct me here, I think but the world of oceanography is still exploding in a lot of dimensions. So we're moving into the whole era of omics, really getting down to the genetic level of things. Now would be the time to get clarity among not just every nation, but every oceanographic entity that goes out to sea to do research. What are our standards and calibration and formats going to be for recording omics, so that every water sample, every cast into the deep sea can be synthesized and brought together? So our efforts and our successes thus far on standards and calibration and data uniformity lag far behind what the challenges of our times and the challenges of the future really require. I come back again, Jeff Bezos made a great speech a couple of years ago to his whole workforce about the API imperative, the absolute imperative for everybody anywhere doing anything in Amazon to adhere to the API standard, so my stuff could connect to everyone else's stuff. And flat out said, if you don't or won't uphold this standard, you're going to leave this organization. That's the sort of maniacal scale of rigor that we kind of need to get to. It's hard. It's terribly hard among nations.
Yeah,
It's even harder among independent research laboratories that are pioneering new instruments and working in a very artisanal way. But I think we have to get there if we're going to. What I want to see us have in the ocean, again, in particular with respect to the living ocean, is the kind of foresight about future conditions that we have now with the atmosphere of our planet. I can tell you what the weather's going to be like here in my hometown 2, 3, 5 days from now with confidence that you can bank on. How do we get to that level of foresight and forecasting, predictability on key attributes of the ocean? That's what this could enable.
That is a good starting point for the physical and to some extent the chemical nature of the ocean, but the biological nature is another whole matter, and it's particularly complicated because of the commercial interest in life in the sea. The fisheries, not about the fish, it's about the fisheries. How many can we kill? How many can we catch? How many can we sell? The commodification of life in the sea. And the estimates, and it really are estimates of how many tuna are there. We have a better idea of how many whales because we can kind of see them at the surface. But how many tunas, how many shrimp, how many of this, how many of that? It's important because we calculate as if we really know how many tons, not individuals, how many tons of whatever animals we're trying to take are allowable, with a goal of having some possibility of a sustainable catch, which is probably not very realistic, but that is now facing a new set of tools with the ability to sample the genetic material that's in the water. At least you can get a qualitative idea of who has been in this body of water by sampling the genetic material that is there, something that we couldn't imagine, I think, even 10 years ago.
Yep.
So we're getting tools that give us better insight to cope with the questions. So we had a question on the table about the law of the sea, and the sea doesn't care. It's law that governs humans in their relationship to the sea that we really need to look at. But given that we have nations that miraculously have come together, at least with respect to assigning jurisdiction over the ocean within for coastal nations, but there's half the world, roughly, high seas, that is truly the global commons. It remains the global commons. And yet, I mean, right now, 2020, 2021, right now, this is a pivotal time when nations are struggling, through the United Nations, struggling with assigning places in the sea that would be protected, where we would not kill the fish, where sea traffic would be regulated in some fashion, the corridors over which the big ships travel, and to try to understand our impact on the nature of the ocean, knowing the connection between climate change and the ocean. I mean, what a breakthrough. That's why NOAA was basically formed in the first place back in the 1970, to bring the ocean community together, put it this way, the ocean community together with the atmospheric community. That it's one system. But what has been missing until fairly recently is the principal role that the ocean has in governing climate. It isn't top down, it's bottom up. It's the ocean really makes possible the climate that we have. And it isn't just a physical or chemical thing, it's a biological thing. And back to the biogeochemistry and the importance of life in the ocean for more than pounds of meat or barrels of oil. It's life in the ocean that captures the carbon. It's life in the ocean that generates the oxygen. It's life in the ocean that shapes the chemistry. And we have been mindful of it to some extent, but when it comes to making policies about protecting our life support system, maintaining Earth as a habitable planet in a universe, far as we know, no place like home, no place that has an ocean filled with life, at least our kind of life. We are children of this planet. Our deepest roots are here. And much as we might wish to transport a colony or even civilization elsewhere, if we don't make peace with Earth and take care of it, we won't achieve those other dreams far out into the future. But the opportunity that now exists to maintain the integrity of the ocean through protective policies where you don't kill the fish, where you are mindful of what you're putting into the ocean, what you're taking out of the ocean, where you respect the most important thing that we take from the ocean is our existence. And to realize that we have to stabilize our relationship with the planet as a whole, land and sea, forests, freshwater, and ocean. But we're further down a level, or have a better understanding of our relationship and the need to take care of the land, trees, birds, freshwater. Not doing a great job, but at least we understand we have to. The ocean seems so big and so beyond what we could get our arms around, that we've neglected it. We put anything we want to in the ocean. We take out of the ocean without thinking about the consequences. But we're starting to right now, back to this being the pivotal time in history, the first time that we have the capacity to understand, and maybe the last time you have a chance to do something about it.
Dr. Earl, that's exactly where I was hoping we could take this conversation. We've spent a lot of time talking about the challenges facing the ocean and the challenges facing those responsible for studying and exploring the ocean, from international cooperation to lack of data and standardization, scientific communication, the economic problems associated with the commodification of sea life. To bring this panel to a I don't want to say more positive note, but I'd like to hear what we can do about it, and in particular, as explorers and scientists, what we can do about it. And so I always thought it was very interesting, Dr. Ballard, your vessel, the Nautilus, the vessel that you've done so much work with, you call the exploration vessel Nautilus, not the research vessel Nautilus, as many other folks do. And so I guess I'd like to hear your thoughts on, as scientists and as you would describe explorers, what can we do about all of these challenges that Dr. Earl just mentioned? Like, what is our role in order to do something about it?
Well, I mean, I may come out of left field on this one, so get ready. We do get, all of us on this panel are commonly asked some pretty tough questions. And I did learn, having served on all sorts of panels and commissions and you name it, that if you give the politicians a choice, they'll cherry pick it. They'll pick one of the easiest things on your list and then feel like they did their job. So when I'm asked this, they say, what's the single most important thing the human race can do to save itself and the planet? I have only one answer: the empowerment of women. And this always catches me. I'm a man saying, I'm doing this selfishly. The planet, if you calculate the carrying capacity of the planet to feed humans, and if you start with them all being vegetarians, which is we're a long ways from that, and America's the worst example. But if you make the assumption that every human being on this planet is a vegetarian, we run out of food in 2050 to feed it. The Earth cannot feed a population that hits 10.5 billion. It just can't do it. Getting back to the calculation that 95% of all humans live on 5% of the Earth. And we build our houses on our farms. So if you look at the loss of farmland, it's staggering loss of farmland just to house people. And so then you get back to the whole issue and the controversy of going away from a hunter-gatherer society in the ocean, which is what we are. Can we farm it in a way that lets the wildlife return? If we as long as we don't drive something to extinction, if we give it a chance, it'll come back. You do hit certain levels. We almost did it with certain species of whales, where you drop below 25, you lose them. You have an extinction. But we're having the Earth has had multiple mass extinctions in life, but this is the first mass extinction created by another creature, and that's us. So it's all about the empowerment of women. And the more you empower women, you get population under control. And that's the only hope we have. So
well,
that's
more minds thinking about the solution as well, right? I mean, if we have the entire population working on solving the problem, we're a heck of a lot more likely to come up with good solutions.
And a third point
that
I would argue from my experience, both of those are true. You get population under control, you get more minds working creatively under the problem. The other point is you will get a shift in the ethos, because if the predominant male dynamic in decision making is competitive. It's get mine, it's maximize, it's accelerate, it's go fast. When you add a large proportion of women to that mix, other value sets, other cares come into play. And to summarize them in a hyper concise way, it boils down to greater care for the other. I mean, just this week, I was talking with an senior executive at an organization that had 2 women vying for a large job. And he decided to split the portfolio between the 2 of them. But as he was interviewing them ahead of that step, at the end of their individual interview, competing for the big portfolio job, each of them talked about the other woman, how competent and capable she was, how ready for the opportunity she was, how deserving of a chance, and how the speaker wouldn't want to harm the other one so badly. This executive commented to me that never would he ever get that kind of concern expressed by a man in that competitive posture. So it is, Sylvia and Bob, I think both have talked about, an ethics transformation. It's a value set enrichment that needs to come to many of these decisions, and bringing women into the decision-making inner circle, into the moments that matter, not just into the scientific enterprise and contributing the data, but at the table where the debates and discussions and decisions are happening. You've got to have a richer set of values in play, or this will not turn around.
We call it Mother Earth and not Man Earth for obvious
reasons. Yeah.
Well, it was
as every ancient culture has done, by the way.
It was Lynn Margulis, who was a partner colleague of James Lovelock. You mentioned the Gaia theory or idea, the concept, Bob, early in the conversation here. But Lynn was perceptive in saying that life on Earth has progressed over the gazillions of years that life has existed, not so much by the Darwinian competitiveness, but far more importantly, through collaboration, cooperation, social structure.
Symbiosis,
absolutely, right down to the cellular level,
right,
which goes right back down to viruses and microbes, and how everything does connect, and far more progress has been made long before there were humans on the planet, and even now, and even among us, through cooperation rather than fighting all the time. It comes with sharing knowledge, advancing. I mean, how did we get to where we are as civilization? People learn things, they pass it along, so the kids of today, 10-year-olds know what Earth looks like from afar. Kids of today know what Einstein, as smart as he was, could not know, because the technology had not reached that level, the communication of knowledge had not reached that level that kids of today now take for granted. And that's cause for hope, I think, that we have the knowledge. The question is, do we have the will? We are infected with this terrible disease called complacency. And it's holding us back from getting to this better place, that if we've got the evidence. We look at climate change. The evidence is right there. We know what to do. We can see, based on knowledge that has been gathered over the decades, looking at the trends. We're not making this stuff up. Do we have the will to take exploration of the ocean? The technology existed in 1960 to go to the deepest part of the ocean. It was 50 years. It wasn't a technological breakthrough. It was a mindset breakthrough. Somebody wanted to do it, And yes, there were some technological advances. And between 2012 and 2019, there were technological advances, but the biggest advance was somebody said, I'm going to do it. And using the technology that existed to make it happen. We have the technology, we have the knowledge. We must come to grips with the fact that the Earth is changing in ways not favorable to us because of us. But because of us, we can go from this to recovery, to finding that place that everybody says we should get to, which is sustainability. But it can't happen with if we have beyond our carrying capacity. Earth is only so big. It never gets bigger. It's just this big. We've got to make peace with what we've got. We can do this. Can we do it? Will we do it is the real question.
So I once asked my old advisor, Dr. Walter Monk, what the biggest scientific challenge facing oceanographers today was. It was actually just a couple months before he passed last year. And I was expecting him to say something, computational, like modeling the ocean, and something about scales of large physical oceanographic phenomenon. But what he said was one word: cooperation. He said we needed to work together better. And that's been the theme that is sort of everyone has been hitting on throughout this entire event. And it's very interesting to me. That being said, we're starting to run out of time. So what I'd like to do is ask each of you for your answer to two questions in just a minute or two. The first, which is something that I myself am very interested in, is what do you think the future of ocean exploration holds? How do you think it will be different than the past? And you can take that in any number of directions. And related, do you have any advice for aspiring ocean explorers, people who want to make their mark, have an impact on all of the challenges we've addressed today? Do you have any advice for them? And so we can go in any particular order. I'll go counterclockwise on my screen. Dr. Walsh, you first. What do you think the future of ocean exploration holds? And do you have any advice for young ocean explorers and scientists who are entering that world?
Well, I think more of us have spoken to large numbers of children than we could possibly count, because all of us are investing on our future. It's as self-serving as hell to get out and talk to the young people, because to some degree, if you can mix the metaphor, they are a tabula rasa, a blank slate, and you write on that. And I say, how many of you would like to really leave your mark on our world? Every hand goes up. And I said, well, come on in, the water's fine. Because on land, yes, there's a lot to be discovered and seen. But every time you dip your toe in the water, as we all know, you're discovering things. It's just amazing. For example, this Hadel work that, the trenches work, biological work. Every time you go down there, they're finding all kinds of things never seen before. And I said, look, if you want to see things as the first human on this planet for the first time, and even give it a nice Latin name after your parents, and go in the ocean. Everything is new. The world of discovery is wide open, and you can be part of it. And by the way, it's fun because when we have conferences, we have them in neat places. And so that's my take. Now, the rest of my colleagues, with Sylvia and Kathy and certainly Bob, have worked a lot more than I have in working with young people in education. So much, it's so important that we turn around and put a hand out and help them come up, because they are our future.
Got it. Dr. Earle, your thoughts on the future of ocean exploration, and any advice or message for young ocean explorers?
Well, the kids of today have good reason to have a sense of despair. You think of all the problems there are, but I say, be glad you are born now. This is the best time ever. What we now know that was not knowable when I was a kid. Kids of today have a head start, and 50 years from now, it'll be the same. We keep learning, and advancing as we go. But the greatest era of exploration is just beginning. We're just beginning to ask to know the magnitude of what we don't know, and what to look for, and where and how to get from where we are to a better place. Getting the physical and biological and the chemical dimensions of the ocean is still a major challenge, but we know enough to know that the ocean is in trouble. It's changed because of us. And those changes mean that we're in trouble. But we are so lucky that we can see it, we can grasp it, we know what to do. It'd be great if we knew more, and that's part of what the next generation will do. Dive in, go find out. But meanwhile, respect what we've got, protect what we can of the systems that are still in great shape. Find those coral reefs that are still in good condition and protect them. And in the deep sea, there's much talk now about mining the deep sea. I say hit the pause button. Just don't do it until at least we understand the trade-offs. We don't know. We don't know the magnitude of the changes that we may set in motion by now turning our attention to mining the deep sea. And we just can't justify the damage against the plus side of the ledger at this point in time. And so the precautionary principle with respect to the next phase of exploration, let's identify those places that we can embrace with the highest level of care, not just the bottom, not just the top, but whole big chunks of the ocean, large areas. How about the high seas? How about if we give half the world a break and say, this is our insurance policy. We need to dive in and learn about the deep scattering layer, about this layer of life, this carbon-rich layer, this place that has such an impact on the biogeochemistry, probably has a major carbon role in terms of influencing climate. We just need to find out. We're not going to have as much luck telling nations that already have their vested interests in the exclusive economic zones. But if the next phase of exploration could be directed to justifying protection, full protection, for half of the world, the high seas that everybody uses every time you breathe, that everybody uses every time water falls out of the sky. Everybody uses all of nature, but we can protect through proactive knowledge and rationale and get the kids engaged, because it's their future that's on the line.
Got it. Thank you very much, Dr. Earle. Dr. Sullivan, the future of ocean exploration and any advice for future explorers?
Yeah, I'm a little more like in Don's vein of things. I think I think the future of ocean exploration is one of invention and inventiveness. I think there's a whole new generation of equipment, of devices, of gadgets to help us better monitor, measure, learn about, study, keep the pulse on the ocean, the bio and the geo, I mean, all of it. And so if you want to jump in a field where you have wide field, wide latitude, to be inventive, to discover things no human being has ever seen or encountered or understood before, things as dramatic, as spectacular as finding another planet in our solar system, I mean, of that magnitude. There are those discoveries to be made in the ocean, and those kinds of inventions to be brought to bear on taking better care of this ocean that makes our planet what it is, that makes your home Earth the viable, livable place that it is. So you can be the inventor, as you can be as inventive as Thomas Edison. You can be as great a discoverer as anyone you ever read about in your textbooks in the great age of exploration. And you want to know why you ought to want to do any of those things, is because your inventions and your discoveries can come along at a point in time where you help change the course of the planet and change the course of humankind's future and your own future. So fun, creativity, the beauty of the ocean realm, and full reign for your inventiveness, your creativity, the excitement of discovery, and the absolute confidence that the knowledge and inventions that you add to humankind's store will add up to the betterment of all human life on this planet.
Got it. Dr. Ballard, the same question, the future of ocean exploration, what does it look like, and what advice do you have for the people who will be entering that world?
Well, your question reminds me of Charles Dickens' Tale of Two Cities. These are the best of times, the worst of times, the age of foolishness and the age of brilliance. I think we have a choice, and it's a choice to be optimistic or pessimistic. And I will always pick optimism. I also love a particular kind of human, and it's a human in middle school. I love going to middle schools more than any other group of kids on the planet, because I know that they are innocent and pure at that moment, and they are born scientists. They just want to know. And I think what I like to tell them is, I say, kids, think about it. Your generation of middle school children will explore more of Earth than all previous generations combined. You are at the cusp of exploration at the most critical time in human history and in Earth's history. So follow your passion and get on with it.
Thank you very much. So with that, we are running out of time. Thank you so much for participating, everybody. Today, we challenged the very definition of the term exploration. We talked about the challenges associated with ocean exploration, everything from the sparsity of data to lack of standards, international cooperation, commodification of sea life, and the challenges facing the ecosystems. The fact that the Earth is not just the Earth's ocean is not just a sea floor, but it has chemistry, it has biology, and we need to understand everything together. And the term ocean exploration needs to include all of that. We talked about the importance of scientific communication and communicating our discoveries to the rest of the world to help make the ocean just a little bit less opaque. We talked about how to solve all those problems too, which largely centered around empowering women, improving education, investing in young people, helping people become passionate about solving all of these problems, and above all, in order to give us the information we need in order to solve all these problems, keep exploring. So I think with that, we're out of time. Thank you so much, everybody. Dr. Sullivan, Dr. Earle, Dr. Walsh, Dr. Ballard. It's been an absolute pleasure and an honor for me to host this panel. Thank you very much, everybody. Have a good afternoon.
Thank you.
Thank you, Chris.
Thank you.
Thank you, Chris, and your very esteemed panel. What a treat for all of us to have this opportunity to hear from some of the greatest explorers of our time. This was really special.
Geography 2050 is free to you, but it does cost a lot of money to make happen. If you've been enjoying the discussions and presentations today, perhaps you'll consider supporting this effort with a small donation. If so, go to www.geography2050.org and click on the Donate Now button. Whether it's a one-time donation or recurring monthly or annual donation, we would appreciate your support. Just know that your tax-deductible donation is going to help advance the cause of geography in America and to instill geographic expertise in our next generation of citizens and leaders. So, donate now and help make the world a better place through geography.
Thanks, Chris. The Maxar Corporation is the developer of the world's most sophisticated network of Earth imaging satellites. Their ability to map and plot what is on the Earth's surface extends far beyond the land. Today, we're going to have the opportunity to hear from the Director of Project Management for Maritime, Mr. Brian Smith. And he is going to talk about identifying illicit maritime activity remotely. Brian?
Hi everyone, I'm Brian Smith, Director of Maritime Product Management at Maxar Technologies. And today I'm going to give you a little insight in what we're doing to identify illicit maritime activity remotely. As you all know, the oceans are vast. Vessels operate dark, masking their activity, making it incredibly difficult for maritime security and enforcement agencies to successfully interdict. If you think about the use cases these agencies are responsible for, having had a comprehensive understanding of vessel traffic is key for successful interdiction, whether it's around sovereignty protection, mitigating IUU fishing, or counter-trafficking. Today, the most common data source for having an understanding of vessel traffic is AIS, but it has its challenges. So AIS is strong because it's a global data set, but it does not capture the complete picture. It's only required for vessels greater than 300 tons. It's easily spoofed, easily turned off, and doesn't work in heavily trafficked areas. And if a vessel does not want to be tracked, its AIS signal will be turned off or spoofed, meaning that if you're relying upon this, you're going to have an incomplete view of vessel traffic, particularly for the vessels that matter most for your end missions. So we at Maxar are applying our capabilities to solve this issue. So taking a step back first, Maxar Technologies is an industry leader in space infrastructure, where we manufacture satellites, where we also provide space robotics, and in Earth intelligence, where we own and operate an industry-leading optical satellite constellation. We provide SAR and optical imagery, and we provide analytics based off of these data sets and analysis, leveraging ML capabilities. So we're taking these kind of capabilities and providing them in an intuitive way to solve these maritime security agency issues. We're introducing a new suite of products, Crow's Nest Maritime Monitoring and Security Solutions, to provide comprehensive maritime satellite surveillance services. So these products include multi-sensor SAR vessel detections, which are great for covering broad areas and detecting where there's vessels, automated tipping and queuing with our optical satellites, which allows you to gain greater insight into the vessels that matter most. We offer optical and SAR port monitoring, and also an application to do all of this analysis within an easy, intuitive interface. We bundle that with expert analysis and training, expert analysis from teams that have significant expertise in this area, providing custom kind of analytics, activity-based analytics, leveraging ML, AI techniques, and also training so that you know how to utilize it within your workflows. Today, I'm going to give a little bit more information on two of those products, multi-sensor SAR vessel detections and automated tipping and queuing. So first, multi-sensor SAR vessel detections. A benefit here is it shows more of the vessel activity in an area, including vessels that are operating dark. Right here, I have an example off the coast of Nigeria, where white and green vessels are those we were able to detect in the synthetic aperture radar, or SAR image, and also correlate to an AIS ping, meaning those vessels are reporting via AIS. Vessels in black are those that we detected in the radar image. However, they were not reported, so they're operating dark. And what you see here is representative of what we see across geographies, just providing an example of how if you're relying just on AIS alone, you're missing a significant amount of the activity in the maritime area. And while SAR vessel detections are fantastic for covering broad areas and determining where there are vessels, there's limitations on the amount of information that can be gleaned. On the right, I have an example of a SAR vessel detection. And as you can see, it's difficult to tell the type of vessel, really impossible to tell the activity the vessel's engaged in, and impossible to tell what vessel it is. So with that, we're coupling our high-resolution optical imagery with radar imagery. So radar imagery to cover broad areas, and optical imagery to hone in on the vessels that matter most. In this example, on the SAR image, what you see is two vessels likely engaged in transshipment. And we use this to tip to our optical satellites, capture the optical image you see here, which shows the Adrian Daria 1 and Jasmine oil tankers engaged in sanctions evasion via transshipment activity. However, when we did this in late 2019 at the time, it was a really difficult process. It was something that wasn't really something we could scale and provide easily for customers. So something more is something we could demonstrate, but customers weren't able to leverage this easily within their workforce. We've since invested in an automated optical tipping and queuing engine that allows customers to seamlessly capture images of vessels of interest. So the way it works is you're able to create rule sets around maritime data sets, things like AIS and SAR-VDS. And when a rule set is met, we automatically capture optical images of those vessels. Let me provide some examples. On AIS, you could set up a rule set around specific vessels that you want to capture images of, specific vessels when, say, they're moving slow. On SAR-VDS, it could be dark targets of a certain size, dark targets within a certain area. We then determine where those vessels are at the time, make an estimation of where the vessels will be when our satellite pass is available. We automatically task our optical satellite, process the imagery, run AI/ML-based vessel detection models, run AIS correlation so that you know which vessels are reporting via AIS and which aren't. We then push the output to our customers via email or via API to their proprietary systems, making it seamless and easily for them to integrate it into their workflows. So let me provide just a few examples of this capability. This first example is a rule set that was triggered off of AIS, where we were tracking known IUU motherships, and the rule set was triggered whenever these motherships slowed down, indicating that they were potentially engaged in transshipment activity. Our optical satellites then captured images of both these vessels. As you can see, there's a vessel next to it, which is offloading its catch into the larger mothership. You can see the refrigerated cargo holds are open where they're offloading that catch. In this instance, even more interesting is these motherships were right outside of an EEZ, and the smaller vessels were operating dark. We'd seen vessel detections from just inside the EEZ, meaning that it was likely these vessels were fishing in an area they were not supposed to, popping out of the EEZ to offload catch, masking the illicit activity they were engaged in. Second example I have is just fishing activity, showing how you can move from just having kind of a dot showing where a vessel is to actually seeing the activity the vessel is engaged in. So starting off on the left, what we have here is an image of a vessel we actually captured in a marine protected area. And as you can see, it's actively person-signed fishing. So you can see the net surrounding the vessel. So you know it's engaged in something that it should not have been. The middle example shows a vessel that was in an EEZ. And this could have been legal, could have been transiting. However, based off of this image, you can tell that from a lack of a weight that it's not moving, that it's either loitering, potentially about to be engaged in fishing activity or meet up with another vessel. Last image we have, you can see the line coming off the vessel. So showing again that it's actively engaged in fishing activity. So it provides maritime security agency the insight they need in order to deploy resources more effectively. Next example we have that shows kind of the power of our industry-leading constellation of satellites. In this example, we have a very high off-nadir image, so a high angle, getting the side of the vessel. And with our high-resolution optical imagery, you're able to see the flag of the vessel, ship lettering, superstructure aspects of the vessel, all critical components of the vessel so you can later ID or identify the vessel, which again is important for maritime security agencies. The last example I'd like to walk you through is of two vessels we captured. We were tracking the vessel on the left, which was operating dark in a specific area. And we then captured an image of a similar looking vessel a few days later in the general vicinity. So at first blush, they look very similar. They have similar vessel shape and draft, similar lifeboat arrangements. However, if you dig in, there's dissimilar deck structures. So with that, the information you're able to glean from high-resolution imagery. You're able to draw some conclusions that it's the same vessel class, but different individual vessels. It's not necessarily or not the vessel that we were intending to track. And while today this is an alpha capability, we are doing it at a global scale. So what we have here is a representation of where we've collected images over 30 days. Previously, you wouldn't see any of these orange dots over the ocean. You really see it just over land. But with this new capability, we're able to capture thousands of images of vessels globally across the oceans, providing much more comprehensive maritime surveillance. While we view this as a strong capability today, our next generation constellation is ideally suited for maritime missions. Its launch is planned in 2021 and will enable up to 15 times per day revisit and triples our 30-centimeter imagery capacity. What this means for maritime missions is we'll have that many more opportunities to capture vessels of interest or vessels engaged in illicit activity throughout the day. We'll also have that much more industry-leading resolution, so you can identify salient features of the vessels, activity the vessel is engaged in, or even identify the vessel. And while I've focused on this capability on how it can apply for maritime missions, this is something that can apply towards land-based missions as well, a variety of different use cases. I'd like to thank you for your time and attention. If you have any questions or feedback, please do not hesitate to reach out to me. Thank you.
Thank you, Brian. Even in the middle of the ocean, somebody is watching. And now we continue with another spotlight featuring Dr. Larry Mayer, who is the director of the prestigious Center for Coastal and Ocean Mapping at the University of New Hampshire. Today, Dr. Mayer will show us how ocean mapping can establish the geospatial context of the rest of the planet. Dr. Mayer, welcome.
Okay, it's a pleasure to be here today with such a remarkable group of oceans. I really couldn't ask for a better context for my talk on ocean mapping, because I think they would all agree that the first step in ocean exploration is really mapping. It's what all the great explorers did, Magellan, Captain Cook. When Jefferson sent out his corps of exploration to explore the continent, they made maps. And I think I have no issue at a meeting of the American Geographic Society to have to emphasize the importance of maps in setting the geospatial context for exploration, for discovery, and for understanding a range of Earth processes. And as I think about my colleagues in the AGS, I look with great jealousy at how easy it's become to establish this critical geospatial context. Modern satellite imaging has given us an unprecedented view of our planet and the ability to look at a range of dynamic geomorphological processes, at cryosphere processes. We can generate quantitative digital terrain models, and we can even look at land cover and the health of forests. It's just remarkable what we can do. And while this was initially difficult to do, it's really gotten quite simple. Nowadays, kind of any 5-year-old can really pop into Google Earth and hit a button, and within a minute or so, just be able to explore with remarkable detail almost anywhere on the Earth. It's just absolutely amazing. But the problem is that this is only for the green and the brown part of the Earth. What about that 3/4 of our Earth that's blue? If we use the same sensors and try to zoom into the rest of the Earth, the 3/4 of our Earth that's blue, we get nowhere. We don't see anything. And that's because the electromagnetic waves that are used in the imaging sensors just don't penetrate very far in seawater. And so we've had to look for other ways to kind of penetrate through that opaque cover that's covering 3/4 of our Earth. And fortunately, through the work of some of the explorers that are sharing the stage today, We've developed these kinds of technologies. We have remotely operated vehicles that can go down thousands of meters and bring the sensors close to the bottom, which is what we need to do because light just doesn't travel very far in the ocean. And so we asked the question, and I've been asked it, what would it take to create a Google Earth for the seafloor, for the entire ocean? What would it take to get resolution on the order of a meter or so, covering the entire ocean floor? Well, we can calculate that. We know the area of the ocean floor. We have an idea of how far light does travel. We know that a typical image only covers a few meters or so in area. And so doing a quick calculation, rough order of magnitude, to cover the ocean, to produce a real Google Earth for the ocean, it would take about, and I don't know what that number is, 600 trillion photos. And if we think about how long that would take to do, we have to get the vehicles down to the bottom, how slow they move along the bottom. Well, there's lots of ifs there, but I guarantee it would be at least hundreds of millions of years. And so the bottom line is that we're just not going to be able to map the ocean at that kind of optical resolution in anywhere near the future. And so people have had to look for other ways to, again, penetrate that opaque mass. And for thousands of years, people have been doing that. They take a look at a statue that was found in an Egyptian tomb from 2000 BC. And sitting up on the bow there is the Egyptian ocean mapper with a hunk of lead at the end of the rope. And so that was the way they measured the depths thousands and thousands of years ago. If I jump 3,450 years, I found a wood carving from the Thames River here. And what are they doing? Exactly the same thing. So for 3,450 years at least, the only way to map the ocean was with a hunk of lead at the end of a rope. But if I jump 500 years ahead and we look at 1940, what do we see? We see, again, exactly the same thing. 4,000 years at least of the only way to map the ocean with a hunk of lead at the end of a rope. Clearly, it takes a long time, and deep water, terribly inaccurate, and of course, very, very sparse measurements. So sometime between the First and Second World Wars, the concept of sonar was developed, recognizing that unlike light waves, sound waves travel very, very nicely in seawater. And by using an echo sounder, we have a way that we can very quickly and relatively accurately measure the depth of the ocean. Now, these first echo sounders that were developed were what we call single beam echo sounders. And so what they did is produce a cone of sound, and that cone spreads, just like if you have a flashlight, and that cone of light spreads out. And it insonifies an area of the seafloor that is something like half the water depth. So if we're in 4,000 meters of water, we've insonified an area of maybe 2,000 meters. And the problem is that you only get one depth return from that entire area, and what returns is the shoalest depth in that area, and it has no angular resolution. So if we have a shoal off on the side, a shallow piece off on the side, we'll read that depth, but it'll be at the position directly below the vessel. And so what we end up with is a kind of a blurry two-dimensional picture of what the seafloor looks like. But again, it was a great quantum leap in capability. And if we take a look, when I was a graduate student at the Scripps Institution of Oceanography in San Diego here, and all the Scripps coming out of the ships coming out of Scripps with their echo sounders, these lines here representing those kind of blurry single beam profiles they collected, the cartographer would come along and kind of connect the dots. And we have here what was literally the best map of the seafloor off Southern California in the 1980s or so, probably into the early 1990s even. Now, about that time, another remarkable technique and innovation came along in ocean mapping, and that was the ability to derive bathymetry from satellite altimetry. It basically works on the fact that the surface of the ocean will respond to the gravitational attraction of features deep below. So if we have a big seamount with excess mass, that pushes up the sea surface. If we have a deep trench with loss of mass or lack of mass, that will actually depress the surface of the ocean. And with an accurate satellite altimeter, you can actually get a rough approximation of the depths of the ocean. But that's the key. It's a rough approximation. It has a very coarse resolution on the order of kilometers and a limited accuracy on the orders of hundreds of meters. And to demonstrate that, because it's revolutionary in terms of what it shows us in terms of the gross distribution of depths and is wonderful for the use of tectonic scale processes, but it's limited in its capability to help us with the real detailed processes we need to understand what's going on in the ocean. And to demonstrate that, I'll use an example I showed in Monaco, where the prince, who's very, very interested in ocean mapping, was there. And if we look at a satellite image of Monaco, we see, of course, with our spectacular resolution, the optical images can provide. I have a digital terrain model that I can drive. This is a 30-meter one. You can go even higher resolution of the area, the same area around Monaco. And we see Monaco Harbor quite clearly. But if I now look at the same image at the resolution we have the predicted satellite bathymetry from altimetry, it looks like that. And I had to apologize to the prince that, I'm sorry, Monaco disappears. And that's the problem we face as we look at the satellite altimetry derived bathymetry, is that it's limited resolution. And so we have, again, the satellite altimetry gives us a wonderful global scale picture of features like ridge crests and trenches. But as we look much more closely, here's a 200 by 200 kilometer area, we see it in this terribly blurry view that doesn't really help us much in understanding processes. And so fortunately, again, about the same time in the 1980s or so, coming out of the military, a wonderful new technology called multi-beam sonar was developed. And what multi-beam sonar does is allows us to use a beamforming technology to insonify a very, very large swath of the seafloor, sometimes 3 to 7 times the depth, the water depth, all at once, and within that swath be able to derive many, many, sometimes hundreds of individual depths with high accuracy. And this really, really changed things. We went from this kind of blurry picture averaging over a large single footprint to now these hundreds of individual soundings across a wide swath. And with concomitant advances in navigation, so we knew where the ship was and we knew where the beams were pointing, motion sensors, because you have this wide swath, you have to very accurately track the motion of the vessel, in computing power and visualization, this really revolutionized our way to look at the seafloor. And if we go back to our 200 kilometer by 200 kilometer piece of seafloor, this is somewhere north of Hawaii, and we take a look at what happens when we just run a single swath through it, we change that to that. And as it says here, what a difference a swath makes. Now we're starting to see things with a scale and a resolution that really allows us to start understanding a whole range of geologic and oceanographic processes. If we go back to our map, our best map of the seafloor of Southern California, and a colleague from the USGS and I spent a couple of months out there with new multi-beam sonars at that time, mapping in that area, and we can change that map to a map that looks like this. And again, this perspective just totally changes the way we look at the seafloor and the way we can understand processes, providing many, many new insights, canyon processes, mass wasting processes, and so on. And so we really have revolutionized the way we can look at the seafloor. But that's not all. It turns out that these same sonars, as they collect the depth information, and this is depth information off of Hawaii, the Big Island here, and excuse me, not the Big Island, this is Oahu and Pearl Harbor sitting out here, going down to about 800, 900 meters off here. That's the depth information. The sonars also record the amplitude of the return, something we call the backscatter, which gives us not a one-to-one mapping, but some insight into the nature of the seafloor. So we go from where the seafloor is in terms of bathymetry to what the seafloor is in terms of seafloor character. And here, if I put the backscatter on, this was an area where they'd been dredging in Pearl Harbor here, dumping it offshore, and you can actually see at 600 meters individual dredge sites, each one of these circular spots, an individual dredge site. So now suddenly giving us a whole new dimension of information about what the seafloor is. This has been used in a qualitative sense also, looking at backscatter here where there are seep communities, a great exploration tool for looking for seep communities. And what we're trying to do now is push this in a more quantitative sense, much like our hyperspectral scanners for the electromagnetic waves. We're trying to look at both the angular response of the backscatter of the seafloor and at the frequency response of the seafloor to try to come up with ways to remotely predicting what the seafloor material might be. We're not there yet, but it's a very hot area of research and something we have great hope for. But as I say on the commercials, that's not all. There's more. The sonars now in the last few years have also allowed us to image in the water column itself. And while originally developed for looking at schools of fish and looking at the dynamics of schools of fish, we've now found tremendous application, much of it pushed by the Deepwater Horizon spill, in terms of the abilities of these sonars to map gas seeps, natural gas seeps, and man-made gas seeps, and oil leaks too. And so there's been a tremendous effort in mapping this with important implications in terms of methane distribution, as these seeps are typically methane, and the methane concentrations in the water column and potentially even into the atmosphere. Now, not just looking at gas, we can also, in shallow water where there are strong oceanographic contrasts, actually use the sonars to take a look at oceanographic phenomena. And here we're seeing on the top a Kelvin-Helmholtz wave in shallow water, and below an internal wave breaking actually in shallow water. And these are in estuaries where there are strong contrasts of water properties, and we can see that quite clearly. But we have been even more amazed that with now broadband sonars, and we're using not the multi-beam in this case initially, but it's what we hope to do with the multi-beam, we can now take a look at really subtle oceanographic phenomena. This is something called thermohaline steps. These result from double diffusion when you have warm saline waters underlying cold fresher waters. And you get these amazing little steps in the temperature salinity profile, and acoustically on the left, we can resolve each one of those steps, in this case, just a few meters apart. And this is really, again, revolutionizing our ability to look into the water column. We can also, where those steps don't develop, see the mixed layer, the thermocline, and trace that for hundreds of kilometers. And we have a graduate student now working on the Baltic, where she's using the same techniques now and has been able to map out the oxygen minimum layer here, corresponding to a beautiful salinity change. And now for tens and tens of kilometers through the Baltic, can map the distribution of the oxygen minimum layer. And so we're really, really coming a long way, but we are not stopping there. If we look ahead at where we're going with these systems, we are always going to be pushing to increase the bandwidth, the frequency content of them. We hope to have chirp multi-beams that give us more information over wider frequency range. We have to start calibrating the multi-beams like we do some of the single beam echo sounders. We're going to see more data density, more solutions per footprint. The more the density, the higher the resolution we can produce in terms of the imagery. We'll see new geometries of the sonars instead of the fan. Why not an annulus that lets us look at the seafloor at different angles all at once? Lots of software improvements, uncertainty improvements, and better processing tools. And I'll mention at the very end a very exciting approach of synthetic aperture sparse arrays coming along. And we're also going to see all kinds of new modes of delivery, particularly with automated systems of our sonars. So I hope I have convinced you that we have come a long way. This is a map that Fontaine Murray produced in 1860 of the Atlantic based on 80 lead line soundings done with a cannonball at the end of a long line, and that was their picture of what the Atlantic looked like. But we have, of course, since that time come a tremendously long way. And here, just looking at the satellite-derived bathymetry, we see this amazing new picture of what the seafloor looks like. But the question is, how much of this do we have that high resolution multi-beam data, the data that really gives us that insight into processes? And if we go to the national databases and look at the global distribution of high resolution multi-beam sonar data, it looks something like this. And when you look at it at this scale, it doesn't look all that bad. But let's zoom into an area here where it looks like it's almost complete coverage at this scale. And if we zoom in, what we see is that it's really quite sparse. And the bottom line is that at this point in time, only about 19% of the global ocean is covered by available multi-beam sonar data. And so 81% of it is not. And what would it take to map the whole seafloor? There's a wonderful project going on called Seabed 2030 now that is trying to facilitate the complete mapping of the seafloor by 2030. We've done a quick kind of back of the envelope calculation, And assuming using current technology, we look at the distribution of depths because those swaths get wider and wider as we get deeper. It gets easier to cover area as you get deeper. We're not looking at water depths less than 200 meters because then it gets very difficult because the swaths get narrow, and we have other potential techniques in shallower water to look at depths there. And we look at two end members depending on the swath coverage and the speed of the vessel. But it looks like something like between 70,000 and 127,000 days. And if we look at a typical oceanographic research vessel at about $45,000 a day, we're looking at a cost between $3 and $5 billion to completely map the seafloors greater than 200 meters. And you would say, who in the world would spend $3 billion to map the seafloor? Well, I'll contend we spend that money all the time on mapping other planets. We send missions to Mars to map Mars. We have most of Mars mapped at 20 meter pixel resolution, a lot of it mapped at 1 meter resolution, and a Mars mission typically costs $2 to $3 billion. And I love the fact that we map Mars. It's critical that we map Mars and important that we map Mars, but you'd think we can take one of those Mars mission effort budgets and turn it towards our own planet. And so for Earth, for 81% of it, that's the resolution we have. So how are we going to get this done? Well, we can convince everybody that let's spend $3 billion and do it with current technology, but maybe we can help reduce that cost with technological innovation. If we look at the distribution of costs for our $45,000 ship, we see that a lot of it is a crew, a lot of it is fuel, and so on. If we were to send out an autonomous vessel, say an autonomous mapping barge, which would have a wonderful form factor for getting a very large array out there, and just think of all the other experiments you can do on that, we would cut down the crew costs. We've already reduced the cost by 30% and cut down many of the other costs. It wouldn't have to come in and out of port. Lots of reductions in costs there. But maybe we can go one step further. Maybe we can get rid of some of those other costs. There's a wonderful new vessel out there called a sail drone. These are autonomous sailing vessels. They collect all kinds of oceanographic information, but they're a little small to put a deep water mapping system. Deep water mapping systems are large and power hungry. But if we could have an autonomous sailing system, we would reduce the crew costs, we would reduce the fuel costs, a lot of the consumables. And again, these things can stay out for 6, 7, 8 months at a time. Well, that was a wish a few years ago. We do now have a 22-meter autonomous sailing vessel that has a deep water mapping system on it. And so we're hoping that could bring the cost down significantly. With a 9-month, 12-month mission, we can have 1.6 million square kilometers per year mapped. And just to show you where we are with this, there's actually it not just in a cartoon, but almost being completed, expecting to be in the water hopefully early in November. You can see the size of this vessel, and that's what you need for a deep water mapping system on the back of it. So everything I've talked about so far has been really just in terms of increasing the technology, increasing the efficiency of collecting the data. But there is something on the horizon which I'm very excited about, which may really demonstrate a quantum leap in capability. And this is a concept that's being worked at Lincoln Labs, and we're happily collaborating with them. And that's the idea of an autonomous sparse aperture multi-beam echo sounder. And the idea is to have a number of small autonomous vehicles, some of them receivers, some of them sources, creating a sparse array. And in theory, and I emphasize the in theory part, this should be able to get us on the order of 1 meter resolution in 4,000 meters of water. And that would be a spectacular advance in capability. So let me bring it to a close there. And what I'd like to do is end with a traditional sunset slide. Oceanographic talks typically end with sunsets. In this case, though, it was in the Arctic, so it's both a sunset and a sunrise, all at the same. The sun just come up, pop right back down. And I think for this topic on ocean mapping, it's really quite fitting, because this is not the end at all of what we're going to see in ocean mapping. It's really just the beginning.
Thank you, Dr. Mayer. It's easy to see why your center at the University of New Hampshire is so well regarded. We move on with a lightning presentation by Mr. Neil Tinmouth, who is the Chief Operating Officer at SeaKit International, and he will look at redefining the way we work offshore.
I'm Neil Tinmouth. I'm the Chief Operating Officer of SeaKit International. The ocean drives the global systems that make our Earth habitable. It's also the mainstay of a global economy, contributing $1.5 trillion and 31 million direct full-time jobs. However, ocean health is declining. If we want a sustainable future, we need to ensure better stewardship of this global resource. Despite being critical to our existence, we know little about what lies beneath the waves. As of June 2020, only 20% of the ocean floor has been mapped. This is changing. With the establishment of the UN Sustainable Development Goals and initiatives like the Nippon Foundation JEPCO Seabed 2030 project, we are now taking steps towards addressing these challenges and building a more sustainable blue economy. However, to achieve this, we need data. Traditionally, this has required large, expensive vessels which burn tens of cubic meters of diesel every day. Large vessels also require a large complement of crew, which need to be changed out frequently, resulting in hundreds of flights per vessel per year, adding to the already heavy operational carbon footprint. But this is all changing. With recent technological advancements and innovations in sensors, satellite technologies, and autonomous systems, we are now able to collect unprecedented amounts of ocean data more cost effectively with a smaller carbon footprint and without putting people in harm's way. Our recent 22-day uncrewed Atlantic mission collected 1.5 billion data points. Being uncrewed, naval architects can completely rethink the way we design ocean-going craft. Without the need to accommodate crew, vessels can be designed around payload, sensor requirements, making them smaller and more power efficient. The result is vessels can cost as little as 5% of a traditional vessel, whilst producing only 1 to 5% of the carbon emissions. For projects like Seabed 2030, which aims to map 100% of the ocean floor, this will have a massive impact on feasibility. Mapping at depths of over 200 meters could take up to 127,000 vessel years, costing over $3 billion and generating millions of tons of carbon. A fleet of smaller, specially designed uncrewed surface vessels could be built and operated at a fraction of the cost with a much smaller carbon footprint. The need for uncrewed solutions has been further highlighted with the onset of COVID-19. With many countries on lockdown, it is a logistical nightmare to get crew to and from the vessels. Consequently, whilst many field research activities have been placed on pause, the US sector has seen a rapid growth as vessel operators and research institutes look for innovative solutions to maintain business continuity. Companies operating uncrewed vessels have been able to continue with minimal disruption as operators control the vessels from the safety of the onshore remote control center. Despite the pandemic this year, we have managed to complete 2 large-scale projects. However, to get to this point, there's had to be a major step change in technology, regulations, and industry mindset. For a USV to operate safely and interact with other vessels offshore, operators need to be able to sense what is happening in and around the vessel. Rapid development of connected sensors now allows operators ashore to monitor the vessel and the surrounding environment to make real-time decisions. As sensor technology has matured, they've become more robust and accurate while prices have decreased. However, as we get an increase of sensor uptakes, it comes with its own challenges, including the increased amount of data which needs to be communicated between the vessel and shore. Vessels operating over the horizon are dependent on satellite communication to transfer situational awareness information from the vessel to the operators, where they assess the information and then send back the appropriate command and control signals. The increase in demand of global connectivity means satellite communication has come a long way. Historically, these systems have been extremely expensive with limited available bandwidths, but in recent years, costs have come down by as much as 60%. Costs and bandwidths are set to improve further with LEOSAT systems, which should bring the cost of high-speed offshore data services in line with terrestrial connections. Regulations often struggle to keep up with the pace of innovation and technology gets tangled in red tape. USV developers and operators must often find novel ways to fit within the existing frameworks. But this is changing as regulatory bodies begin to see the value of uncrewed vessels and increasingly support companies by providing flexible frameworks to safely test and demonstrate the capabilities. Since CICA was part of the winning JEPCO Nippon Foundation alumni team entry in the X Prize competition, we have seen a rapid increase in USV capabilities, including the development and deployment of more complicated systems such as ROVs and AUVs. However, there is plenty of room for continued development before we see USVs becoming industry norm. So what does the future of USV technology look like? To accommodate the ever-increasing volume of data being collected, there will be a growing shift towards edge computing and AI data processing, along with improved autonomous functionality and capabilities, including collision avoidance. This is already becoming a reality with the development of systems like Teledyne's Mira AI, which was used to process multi-beam data on board the vessel during our recent Atlantic mission. Uncrewed vessels are set to play a prominent role in the future of marine survey and inspection, and we're starting to see wider adoption. Remote technologies will deliver significant benefits to everyone involved in the marine sector, bringing about faster, more efficient, and safer marine operations at a more sustainable scale.
Thank you, Neil. Project Geospatial is a podcast and movement dedicated to increasing awareness of geospatial technology, industry best practices, and community resources. Under the direction of Mr. Adam Simmons, Project Geospatial partnered with the American Geographical Society to produce this virtual symposium, and we are indebted to Adam for all of the effort and resources he contributed to make this symposium possible. Ms. Paige Roberts is with the One Earth Future Foundation, and she is here with us today to present a lightning talk on their work to map the Somali coastal resources. Ms. Roberts?
Hi, I'm Paige Roberts with One Earth Future, and I'm presenting today on Project Badwain. Badwain means ocean in Somali, and while interest in Somali marine resources and their economic potential is increasing in the region, little information is available about the current state of the marine environment there. So we created a platform to show what is available and what's possible with existing data sets as a place to attempt to fill some of the knowledge gaps that exist with new data that is coming out of the region. It's a free online interactive tool to map Somali coastal resources and maritime activities. Project Badwain is meant to be used by a variety of stakeholders to inform policy, education, and international and private investments. And the hope is that it can be used in multiple ways to help view interactions about resources and human activities and where those interactions may turn into conflicts and creating some plans to avoid those conflicts. We also hope to provide some information about the Somali marine environment, create some holistic management measures, and engage the community and foster collaboration. As we all know, there are a variety of uses co-occurring in the marine and coastal space, and being able to identify where interactions might happen is useful for management planning efforts that are really at their beginning stages in the Somali region, but are gaining a lot of traction. Project Badwain includes a mix of publicly available information and original analysis. We include habitat information from outside sources, as well as fish catch and ranges of commercially important species. These data are from the sea around us, and that's the best estimate we have right now for fishing in Somali waters by the domestic fleet. Combining fish catch ranges with a complete map of coastal towns and landing sites and their approximate sizes gives us a good picture of the domestic fishing sector in the Somali region. And when combining those landing sites with foreign trawling areas, you can see that there is the potential for some conflict to happen there. Illegal, unreported, and unregulated fishing is one of the major causes of conflict in the region, and you can see why with overlapping ranges in fishing and also in species overlap between the domestic and the foreign fleets. Other marine uses are also included in the map, like shipping lanes and ports, which are useful proxies for pollution and traffic in an area that might impact domestic fishing and the marine environment. The website includes some informational pages and supplemental material outside of the main map. This is one example. It's a supplemental map of all of the international development and donor work that's happening in the region around fisheries and coastal conservation. It's useful for coordinating our work and for others to coordinate with each other. Combining those international development efforts with the landing site data, we wrote a report that identified coastal communities with large fishing populations, but without very much attention paid by the government and international development and private investment communities. This report informed Secure Fisheries work facilitating cooperative management in locations in Somaliland and Somalia. In the near future, I would like to include some more educational materials about biology, ecology, and fisheries in the region so that it's a useful resource for anybody seeking information about fisheries off the Horn of Africa. We also want to take it down to the community level and go from this large-scale regional view to a much more locally focused one. This is a community-based mapping effort that we conducted in one of our cooperative management communities. And building environmental knowledge will help foster ownership over their own resources and empower people to manage their resources locally. I'm also planning to integrate some new and exciting data that we're starting to collect, including some shoreline mapping and fishing locations. So you can explore the map for yourself at securefisheries.org/Somali coastal resources.
Thank you, Ms. Roberts. John Pepper is the chairman of OceanWise, a leading geospatial provider and manager of marine environmental data. Today, he brings us a spotlight presentation on making waves in marine telemetry. John, welcome.
Good day. My name is John Pepper. I'm chairman of OceanWise Limited, a company based in the UK. We are experts in data management. My talk today is aptly named Making Waves in Marine Telemetry. A quick diagram here to show you what OceanWise does. Each of the pictures represents an element of our core business. We're effectively data management specialists, governance being at the center of what we do, in the center of the wheel that you can see, and also the four activities: monitoring, training, software, and mapping, geospatial mapping. Today, we're going to concentrate on environmental monitoring and specifically telemetry. It may not be a term well known to everybody in the audience, but it's the automated communication process whereby remote data is transmitted from instruments and sensors back to a receiver. Marine sensors are devices used to measure environmental data across the world in a wide range of environments, typically covering tides, currents, waves, weather conditions, air quality, and a host of other parameters. But instruments need to read a stream of numbers from a sensor and turn them into engineering and scientific units. That's all part of telemetry. A logger is required to store units, or a storage unit is needed to hold data locally. And instruments can relay data to multiple loggers. And a logger does not have to be a database. It often is in big organizations, but it can be as simple as a USB memory stick. Standard telemetry units only transmit data from single or multiple sensors. But remote telemetry units, and we'll be talking about that today, can transmit and receive data not physically connected to the place where the instruments and the sensors are located. And really, telemetry provides fast, reliable, and secure environmental data transmission and receipt from really anywhere to anyone. So why is it important in the marine environment? Well, three big things are happening at the moment. Climate change is leading to an increase in unforeseen environmental conditions occurring. There's a fast-growing need for reliable, accurate and timely environmental data by ports and harbours, for example, in their vessel traffic services, by shipping, increasingly using e-navigation, electronic navigation, offshore energy, in the wind farms, oil and gas industry and tidal sector, fisheries, scientists and coastal conservation sectors. And a means of retrieving data from a range of sensors can be shore-based, on the surface, on board ships and boats, in the water column or on the seabed. So these sensors can be anywhere from above the water level to the seabed. Telemetry is valid in all of these particular environments. So data collection. Data is all collected for a purpose, and I'm sure as a geographic audience you know that, because it's expensive to capture. So location at which the data is collected is rarely the place where the data is assessed and acted upon in telemetry because of the environment in which the measurements are made. It may often be below the water surface or in very remote and hostile locations. Decisions are made using that data at different times and places in the operational process. Telemetry typically uses radio-based systems to transmit, allowing communication across different platforms, such as satellite communications over the horizon instances, marine systems for safety of life at sea, SOLAS technology, shipping mainly, and also land-based systems where cell phone technology can be used. There are four types of monitoring. Very simply put, there is operational monitoring, which is effectively routine and ongoing readings of tidal behavior, wave height, wind speed, direction, currents, and visibility. And is typically used, as I mentioned a minute ago, by port pilots and wind farm operators. And they're interesting conditions prevailing ideally within the last 5 minutes. It's a constant way of monitoring. And delivery time is critical, where that data is required in front of the decision maker within 5 seconds. You've then got long-term monitoring, which associated perhaps with sea level rise baseline studies and wave and wind climatology. It may be multi-parameter and multi-instrument, where every record is critical and the frequency of data delivery is not so critical. It can be daily uploads. Such things of studying wave and wind climatology is over the longer term. Short-term monitoring, where you've got multi-parameter, multi-instrument, adaptive sampling and or transmission with variable frequency during periods of deployment. Every record is critical and the frequency of data delivery is perhaps not so critical. And then you've finally got responsive monitoring, dredging and engineering projects and tsunami warning systems where you are responding to a particular challenge by monitoring for, again, a set period of time, where data is collected and automatically assessed, and it may be in response to a warning or an alarm transmission that monitoring takes place. Trend analysis is then produced, processing on board the device that you're using, which has an interest in the conditions prevailing within the last 5 minutes, for example, and what will happen next is a key objective, certainly if we're into tsunami warning. And also delivery time is highly critical. So when you're thinking about designing a monitoring network, the design considerations are very important. Measurements relative to where the users the information, is it point to point, one to many points, or many to many? And in doing so, the system power budget and the services requirements and the site locations have to be borne in mind. Data transmission budget is also important. What are you measuring? When do you need the result? And what will the cost be? Another element is data security, reliability and confidentiality. A lot of monitoring that is done is not open to public scrutiny or indeed for general reuse and is kept confidential for operational or defence purposes. You've got data redundancy and duplication, where repeater stations and paired sensors may be required. Data latency, where stamp time data, as it is measured, but not on arrival at the server. It's actually arriving later because of latency in the data. And clock control. And GNSS is typically used to achieve time synchronization of all data passed across the network. It's also important for controlling transmission via satellites such as Meteosat or GOES. The accuracy of data required. Now, that's a function of the sensors, not the network on which the information is being stored. But it does have an impact on the network design, because if the accuracy is higher, it will require a much tighter network design, a robust network design. Multiple lower cost sensors can give redundancy and cross-checking of data, but fewer high-end sensors gives a smaller amount of data transmitted, but more reliance on individual sensors and less ability to monitor drift and fouling. So it's really high-end sensors give you very small, a smaller amount of very high accurate data. But the note at the bottom, sensor calibration regime is always key to delivering accurate data. Transmission methods. There are a range there, serial, RS-232, 422 or 485 or USB or Ethernet and broadband are relatively common transmission methods. They're called direct communications. But out in the oceans, we may be forced to use UHF or VHF radio networks because of the distance involved and also the surety of the signal in getting the information from the sensor back to the shore. GPRS may be used. Satellite for over the for long distances, Iridium, for example, Inmarsat, and the use of satellite broadband, very important. I mentioned Meteosat and GOES for broadcasts. That's another legitimate method. Increasingly, around ports and harbours and around shipping, the automatic identification system, AIS, is starting to be used. And then you've got LoRa, the low power wide area network technology. So a range of transmission methods are actively used, dependent on the location and the requirement for the data to be delivered. The protocols depend on what service is available at a chosen location, which I've just mentioned, how much data you need to transmit and how often the transmission should take place. But just as an indication there, you've got SMS, email, file transfer protocol, HTTPs, TCP, UDP. These are terms that a lot of us already know, and AIS, but you need to be aware that more data will lead to higher costs, more frequent transmissions will result in higher costs, and more remote locations will result in higher costs. So it's important to select the protocols which match the complexity and the volume of the data, as well as the delivery mechanism. So powering the network is a controlling factor. and you run the sensors and power the transmission with no problem on shore, and remote sites, though, can be a challenge. Running sensors and power to power the transmissions. Energy required versus the storage limitations. Servicing frequency for battery replenishment, for example. The size of the scientific payload. Batteries are big and heavy. The stored power sources, the batteries themselves, how they can dictate how the network is controlled. And replenished power sources, such as solar panels. They can be efficiently based on latitude, season, and size of panels that can't be used everywhere. If there's permanent darkness in the North and South Pole, then that would not probably be a useful method of powering your monitoring stations. Wind generators and wave energy converters are also an issue, and servicing. And the note at the bottom, how hard telemetry has to work, e.g. finding signals to transmit the data, is a key factor in power demand levels. So just to give you an indication here, this is a site map of a large area in the Thames Estuary that OceanWise developed. Sensors are marked by descriptions in the south of the River Thames Estuary and also well into Essex on the north side of the Thames Estuary. And those dotted lines and those single green lines and red lines indicate the communication between each of the sensors and the delivery of the telemetry using a transmitter north of the River Thames as a way of strengthening the signals. The mapping side of it, we provide anyway, and there's a URL there if you want to have a look at that once the presentation's finished. But that's the site map for the Port of London that we are actually managing for them as we speak and have done for the last 8 years. So the transmitted data. Messages have to be structured to ensure the data is both well described and complete in terms of what is being sent, where it's coming from, and where the data is collected. Error checking provides a means of ensuring the data is integral and not duplicated. Checksums, you have to think about checksums, sequential checks, looking out for missing data, timestamps, and duplicate data. So that's things to consider when transmitting data. And delivery can be in real time, critical for operational responsive systems, our customers, certain ports and harbours sector, and also those that are looking at disaster management, require data coming in as soon as possible after that sensor has recorded that information. There is a cost impact, the data is mission critical, and every record must get through quickly. We've also got near real time, where delivery is good enough for many applications. And again, it depends what that application is. You may not need instant real time information if you're managing or measuring currents and waves. Cost savings can be made by batching data together for periodic transmission. So let's look now about how data telemetry, marine data telemetry, is becoming smarter. And this is down to 4 particular aspects. We are one of very few organizations that can deliver smart telemetry. A lot of telemetry is available, but it's very much sensor dependent, where the telemetry only works with the particular instrument or the sensor. It has to be remotely managed and configured to be considered smart. It's a key asset or aspect of it. Smart telemetry, data telemetry is power efficient. It's important for buoy-mounted systems and off-grid solar power systems. You need to be able to reformat incoming, outgoing data, legacy and new instruments, feeding legacy and new systems, and also it is cost efficient. It uses multiplex data streams to reduce the data transmission costs, power consumption, and also provides station metadata. Very important that, as with all geospatially related data, the metadata, the data about the data, is important, increasingly so, but was not considered so until a few years ago. Smart data transmission, again, configurable, works with any instrumental data type, it's swift, it reduces delays, it's intelligent, with the system checks that messages have been delivered correctly. It allows for compression of transmitted data. Flexible, not restricted to one data delivery mechanism, configured to use a variety of protocols. It has to be robust to cope with the transfer of different data volumes and different data modes, and has to be secure, reliable, and confidential. And our answer to that is the IP buffer that we developed in the UK with a partner around about 8-9 years ago. And we have been upgrading it ever since. This is quite unique, and we're very proud of it. It works seamlessly with port log, that's porting information and logging it in longhand. And that's Oceanwide's environmental data sharing and publishing platform. And it's been proven to be so reliable across the world in over 200 locations, in temperate climates, in harsh conditions, in ice conditions, in desert, and also in areas where harsh weather conditions such as hurricanes and tropical storms occur. The low telemetry unit has low power consumption. It's programmable for the data acquisition and can be programmed remotely. We do a lot of programming remotely once it's in situ. Choice of data delivery options works with a wide range of sensors and enables bidirectional communication and remote device administration. And it's safe and secure for the transmission of the data. There's an image of it there at the bottom right-hand corner, and just an image on the above it showing how a port pilot may receive some information. So the features of Portlog: online storage and publishing solution for environmental data acquired by differing monitoring techniques and sensors. It displays data, both real-time and historic, from a single or a number of sites. And it presents dashboard displays, very important this, of the latest information and observations, e.g. for tides, winds, waves, from all available sites, plus time series of historical data from selected sites. The dashboard pages display the ages of the data received and the system information, such as the battery levels and signal strength, for engineers to determine transmission faults and diagnostics. And an interactive map displays our provider of all the sites. And we are now providing map displays to all of our customers. Again, there's a website there where you can look at a new video that we've just completed in the last few weeks. Right, just to round off, I want to talk a little bit about Associated British Ports Group, ABP Ports Group, which is the largest ports operator in the UK. They've been a customer of ours for a decade, or 10 years, and they're using IP buffers to telemeter real-time environmental data transmitted and received centrally from sensors at or near 23 ports right across the UK, from Scotland to Wales, to the south coast of England, to the east coast of England, and doing so in a smart, reliable and secure manner, all displayed using Portlog. And there's a few images there just showing what the harbour master, who is pictured in the top image, can see on his dashboard. And we will provide dashboards in the colours, schemes, and the design criteria that the customer requires. So no two customers require the same sort of format for their dashboards, believe it or not. And here we've got a picture of the networks that we are working on, or have been working on. We're still working on them at the moment. And here we've got a typical network design for that ABP network. And you can see now that I've just superimposed the geographic regions that are components of this network diagram that we produce. And that is how the whole thing's managed. We've got the port log server at the centre in our offices in the south of England. We've got the South Wales ports, the Humber ports, very, very important on the east coast. Southampton, a major cruise terminal and container terminal. And we have just completed around about 10 short seaports in the northwest of England and in Scotland for ABP. And this is a simple diagram to show how the buffers work, the IP buffers work across that network, where you've got each of the situation, each of the locations, and you've got the mode of transmission. You've got radar, local area networks. We're streaming via the APN and the receiving stations to a port log server, and we're creating a wide area network for the customer, firewalled, of course, in this particular case. Here we've got a couple of dashboards, copies of the dashboards. These are the Southampton water tide gauges, and as you can see from that, it shows each of the stations down the left-hand side, and these, the wind direction, speed, gust speed, tide, and visibility, which are constantly changing. It's a 10-second upgrade of the data in Southampton for these parameters, for these environmental parameters. And just an example of if things go haywire during we can immediately find where faults or readings are being missed. Data is not being shipped in, and we then have a set of diagnostics where we can go and look at those particular stations and look at where the problems are occurring. And to finish off, this is at the other end of the spectrum. This is not a port, although it's a coastal area. This is a sea level project that was completed last year. There's a few images there showing where it is, but we're looking at Dominica. There's the island, and there were two old existing observing stations that were considered redundant, and the new one was put in place over on the coast facing the Atlantic, because that's where most of the wind direction, storms and hurricanes emanate from. And in 2017, just after we'd started the work, or in the process of doing the work, two hurricanes struck in very quick succession. Hurricane Irma, Category 5, late August, early September, and then almost within days, 4 days after Irma, Maria came along. The worst natural disaster on record to affect the island of Dominica, the US Virgin Islands, and Puerto Rico. And you can see the track on the right-hand side of the screen there of both of those. The point I'm making here is that the Marigo, which is the station that we put in place to monitor the weather conditions, tracked Irma in real time. It was providing information back to the customer in near real time throughout the period of Irma, and then was called into action again a few days later with Hurricane Maria. What you will notice is that the graph goes off the top of the z-axis because we had extremely difficult conditions in that second hurricane. And it left us with some challenges, but the outcome of this was totally unforeseen. Communication with the sensors and transmission that we got on the island in Dominica was lost on the 18th of September at 21:49 AST, where all power lines came down, all the telecoms came down, and no contact from Dominica was received for 4 days. The island was destroyed practically. GPRS comms However, were restored about 7 days later, and then out of the blue, the IP buffer received all the missing tidal and net readings retrospectively and backfilled all of the data in the information that was provided to the customer. We didn't expect it, they didn't expect it, and not one single reading was missed, even in that Hurricane Grade 5. With that, I'd like to thank you for following what I've been talking about. I hope you found it interesting, and I hope that you'll have a chance to go perhaps and visit our website, oceanwise.eu. Thank you for listening, and thank you for watching.
Thank you, John. That was great. We now return to our lightning presentations, and we'll hear from Ms. Jennifer Wozencraft about utilizing cutting-edge tools to map the coastlines of Alaska.
Hi, I'm Jennifer Wozencraft with the U.S. Army Corps of Engineers. I'm Program Manager for our National Coastal Mapping Program and Director of the Joint Airborne LiDAR Bathymetry Technical Center of Expertise. And my lightning talk today is about mapping the coast of Alaska, some work we've done in the past couple of years and some work we have coming up. The Joint Airborne LiDAR Bathymetry Technical Center of Expertise is a 22-year collaboration among the Corps of Engineers, U.S. Navy, National Oceanic and Atmospheric Administration, and U.S. Geological Survey. And our mission is operations and R&D in airborne LiDAR bathymetry and complementary technologies to meet the airborne coastal mapping and nautical charting requirements of the partner agencies. We've developed 3 different generations of airborne LiDAR bathymetry systems, and the one we used in the state of Alaska is called the Coastal Zone Mapping and Imaging LiDAR. It's our most recent LiDAR bathymeter that we fly with aerial photography and hyperspectral imagery. We fly at about 400 meters altitude with a 300-meter swath under the aircraft. And our primary limitation for the green laser system is turbidity in the water column. We've used the JALBATEX capabilities, the CSMIL, in our National Coastal Mapping Program in the lower 48 since about 2004 to collect regional data sets to support regional sediment management in the Corps of Engineers. We're currently on our 3rd cycle around the coast of the U.S. and are starting to integrate Alaska into our program. In 2018, we took advantage of a Navy aircraft transit through the state of Alaska to do a pilot project on Homer Spit, which is a spit across the mouth of the Kachemak Bay, where the Corps of Engineers has a navigation project with a local harbor and some shore protection projects as well. It's about a 4.5-mile long gravel spit where there are also some other resource management interests there too. We flew about 14 hours of flights over the spit. You can see the flight lines and the data that we were able to collect. We collected at 2 different tide cycles, high and low, to manage turbidity, and we're able to see about 19 meters depth along the spit with a gap along the shoreline where there was some suspended sediment. The challenges that we discovered, we knew we'd have a short survey season in the state of Alaska with remote survey locations, but the weather changed hourly to daily. You can see that in the slide here. We had terrain near our survey area, as well as some submerged aquatic vegetation and suspended sediment in the water column that we had to manage while we were processing the data. And you can see a turbidity plume and the aircraft flying there to demonstrate that. In 2019, we expanded to a larger operation where we were looking at addressing some requirements for data for tsunami modeling and coastal storm modeling, as well as the Corps of Engineers navigation and coastal erosion issues. And that was all collaborative with the Alaska Coastal Mapping Prioritization product. We selected our areas based on probability of success and picked 13 of those. We had 3 different bases of operations, Nome, Anchorage, and Juneau, and surveyed for about 13 days on those projects. And you can see some of the data that we collected there. And that data was delivered in December following the summer that we collected that. And this is an example of one of the tsunami modeling sites, Seldovia. You can see in the digital elevation model, the airport and the harbor, as well as some beautiful bathymetry there, our wingtip photo, and also our standard data products that are point data, digital elevation models, our aerial image mosaics, as well as hyperspectral imagery. The Latuya to Palma area was flown out of the Juneau base of operations, and this was more of a typical coastline survey like we'd see in the lower 48, except we had glaciers, which you can see in some of the pictures there. So it's beautiful area of the country to survey where we can make some really beautiful data to support the coastline data needs of the state of Alaska and federal agencies there. Elfin Cove was one of the Corps of Engineers projects that we surveyed. A lot of the Corps of Engineers requirements were related to needing data to support development of infrastructure for Alaska coastal communities, and this was a navigation project example. I think that we also flew out of the Juneau area. And the next thing we want to do as we expand into mapping more areas in the state of Alaska is to bring some of our National Coastal Mapping Program products and tools that we've developed to support the slew of applications that you see on the right-hand side of the slide there, looking at developing coastal metrics, vegetation maps above and below the water surface, change detection toolboxes, and looking at our coastal structures in a systematic way in the state of Alaska. So bringing those capabilities there. That's all I have.
Thank you, Jennifer.
Do you love geography so much that you want to spring to become an AGS fellow? Or would you like your company to sign up as an AGS corporate angel to support our geography education initiatives and so that you can become an AGS fellow designated for your company? Well, that would be great. If so, go to www.americangeo.org to join AGS now. But for those of you who aren't really joiners, you can still support the cause of geography with a small donation. We at the American Geographical Society are committed to building geographic expertise in our next generation of citizens and leaders. If you would like to support this cause, please go to www.geography2050.org and click on the Donate Now button. Whether it's a one-time donation or a donation that you set for a recurring monthly or annual payment, we would appreciate your support. If all of you watching today chose to provide just $5 each month, it would have a transformational effect on the American Geographical Society's support to geography teachers and students across this country. So, donate now and become part of the future of geography in America.
Thanks, Chris. Our next lightning is about detecting hidden maritime activity and is presented by Mr. Kevin Moyer, who is the Director of Strategic Partnerships at Hawkeye 360. One of the world's leaders in spectrum-based geoanalytics. Kevin?
All right. Hello, everybody. My name is Kevin Moyer, and I lead strategy for Hawkeye 360. We are excited to talk to you today about how we're helping detect hidden maritime activity that formerly went undetected. There's a lot going on across all the world's oceans, and as we all know, not all of it is good. Illegal fishing, smuggling, piracy, sanctions violations, these are all hard problems, and they're getting worse. So a lot of folks wonder, how do you go about understanding and preventing that illegal activity? Well, until now, you could send ships or aircraft to go investigate. You could take satellite images of ships at sea, whether that's electro-optical or synthetic aperture radar. You can track vessels using satellite-based AIS. And now there's a fourth tool in your toolbox called RF GeoInt. So it turns out that most of the activities we're concerned about require the people doing them to use electrical devices that give off RF energy, such as radios, radars, satellite phones. Ships need to navigate, they need to communicate in order to do what they do. The RF emitters they use to do those things can be geolocated and analyzed. At-sea transshipments, dark ship activity, illegal fishing, all can be identified by the RF signatures of the vessels conducting those activities. Because of the nature of how RF waves propagate, they can be geolocated and detected over a huge area. So imagine being able to detect, for example, all of the radios and radars operating across half of an ocean, let's say the Mediterranean, in a single 8-minute satellite pass. We can do that. That is real right now. Monitoring whole oceans for human activity on a daily basis is now within the realm of the possible and the affordable. If you are passionate about sensing and mapping the oceans, this is a really powerful tool to have in your toolbox. The slide you're seeing right now shows 20 million independent geolocations that our satellites have completed in the past 2 years. How does this apply to the challenges you're facing? This is an example of an Iranian oil tanker flotilla that was trying to evade being detected. So as soon as they left Iranian ports on February 23rd, they turned off their AIS, and you can see that red track on the left. And they came back up on AIS as they passed through the Suez Canal, but then went dark again. Working in collaboration with Planet and with tanker trackers and using our RF data, we were able to figure out when and where they arrived in Syria to offload their oil. So the video you just saw shows how powerful RF data can be in understanding maritime activity that folks would rather you not know about. So, for example, when fishermen go fishing out in the ocean, they often try to get fish wherever they can, and frankly, the oceans can be a bit of a Wild West scenario sometimes. They can turn off their AIS and hide. EO or SAR imagery is the scope, the aperture of those capabilities is fairly small, and so it's hard to know when you're going to take one of those shots that you're going to actually see a ship, coupled with the challenges of clouds and other things. So that video nicely shows where you can see ships acting at sea based on their various RF emissions, and then go tip and cue other capabilities to figure out what is actually going on. So in closing, we're just excited to show you today a new way to sense and map what's going on around the world's oceans. Thanks for your time.
Thank you, Kevin. And now we come to our book review of the day. And here to tell us about their latest book is Dr. Dawn Wright and Mr. Christian Harder from Esri. Dawn and Christian.
Hi there, I'm Dawn Wright, Chief Scientist of Esri, and my colleague,
Christian Harder, also with Esri, specifically content strategist and writer and editor for Esri Press.
And we're so very pleased to be invited to the American Geographical Society's book talk. And we are here to talk about our latest book that we co-edited together. It's called GIS for Science, Applying Mapping and Spatial Analytics. And we're going to use the time today to go through this book with you, to give you some background on how the book came to be, to talk about the various stories that are in the book, the design elements, and also the supplementals that go with the book. So I'm going to start off just by giving a very brief introduction to how this book came to be. And I'm going to pass off to my colleague, Christian, at that point, and we're going to go through various chapters in the book that are very specific to oceans, especially given the Geography 2050 ocean theme of your conference this year. So first of all, GIS for Science is a book that we think is very timely. it was commissioned by our CEO, Jack Dangerman, because he really wanted to have a book that showcased how scientists are using the power of geographic information systems to solve real world problems. And so the power of this book is that it is actually written by scientists. And there are all kinds of wonderful examples of our human impulse to solve problems, to discover things about the earth, things about how we are using the earth, ways in which we are observing the earth. In fact, the book is separated into these different sections that focus on those activities, and also how geography and GIS can provide an objective platform for effectively conducting and sharing scientific research. So the goal of this book is to spotlight the amazing work of scientists around the world in various scientific disciplines. In fact, this book, GIS for Science, with this orange cover, is the sequel to the first book that came out last year, GIS for Science, Volume 1. Now, in the pages of these books, you will learn about sustainable precision agriculture, geological processes beneath the earth, disaster response, ecology, all kinds of topics. But we wanted to first start off by telling you a bit about the cover, because this second volume of GIS for Science has some very powerful ocean content. And what you're looking at here on the cover is a very different way to view the ocean. This is actually a map that was based on the work of Athelstan Spielhaus. If you're familiar with Spielhaus, you know that he was a very distinguished meteorologist, but he was also an oceanographer, an inventor. He designed the very first bathythermograph. He designed a weather balloon that was actually mistaken for a UFO over Roswell, New Mexico. He was actually involved also in designing some of the skyways of Minneapolis, Minnesota. But one of the things that he did in 1979 was to conceive of this map that you're seeing here that shows all of the oceans as one interconnected ocean. And this is often referred to as the Spielhaus map of 1979. It was very popular at that time, and it has come back into vogue, especially now as we're talking so much about how we need to conserve and better manage the ocean as one body, and as we go into the UN decade of ocean science for sustainable development. Now, the challenge with Spielhaus's work is that he never did the mathematics to actually make this into a projected coordinate system so that it could be used in modern computerized mapping systems like GIS. Well, interestingly enough, JCOM came to us at ESRI. JCOM is the Joint Technical Commission for Oceanography and Marine Meteorology. It's a group that leverages the World Meteorological Organization as well as UNESCO. They came to us and said, can you, and they're a heavy user of our ArcGIS software, and they said, can you please help us to be able to use Spielhaus, this map, in GIS, specifically in ArcGIS. So our projection geometry team did the mathematics necessary in order to make the equivalent of a Spielhaus projected coordinate system. It's actually based on the Adams Square 2 map projection. And in this way, this is now in ArcGIS software. You can recreate this map as a base map. You can put other layers on top of it. So this is where our cover derives from, because you're looking at the Spielhaus map. Overlain on top of it is the world ocean floor geomorphology. And later on in the book, you can actually see more about how this projected geometry system came to be in the technical showcase section of the book, which talks about some of the innovations that ESRI staff specifically have made toward GIS. But now to pass over to my colleague, Christian, one of the things that's really powerful about this book is the way that the stories are told. And Christian, would you like to talk about the layout of the book in terms of how you, as the designer, approach this? And maybe we could go to the first ocean-based chapter, or how would you like to start off?
Yeah, we can go to the first ocean chapter. I think that's the USGS work, Roger Sayre's work.
Mm-hmm.
One of the kind of guiding principles of this work was that we wanted to make the work of these scientists accessible to a broader audience. In other words, we didn't want to just write another research monograph for other scientists. We were trying to make a book that would appeal to a much broader audience of GIS professionals, people in the Esri ecosystem, and also just a general audience of people in the world that are interested in science and the world around them. So we came up with a large format, kind of almost a coffee table format. And the idea was that we would fill the pages with rich graphics, well-edited text, not a lot of text, more kind of graphically oriented. Dawn, you can just maybe start paging through here. This particular chapter, I'm kind of jumping ahead here into the content a little bit, but this is the work of Roger Sayre and the USGS and Esri around the kind of cataloging of all the islands in the world. So what was the actual number? 380 something thousand islands. Dawn, was that?
Yeah.
So
yeah, and this was actually part of our project to create a global ecological coastal ecological units system.
Right. So up until recently, believe it or not all of the islands of the world had ever been captured into a geographic database. So this chapter gets into a little bit of the history of islands as they've been mapped through history. Keep paging through, Dawn. And okay, starting in here, we start getting into the first efforts to actually digitize and capture the world's islands. And so you can see here the kind of progressive improvements in accuracy that have been made over the years. And if you page one more page, so this is kind of where we are now in terms of spatial accuracy. If you can imagine the work of digitizing 380,000 islands greater than 1/2 kilometer in area, I believe was the threshold. It's a huge amount of work, and it wasn't done fully automatically or fully manually. It was kind of a semi-automated process using satellite imagery and other remote sensing data sources to compile this data. So this chapter is really a little bit about GIS, but also a little bit about the kind of history of the geographic study of islands, and then it also kind of segues into some of the applications of this data. And now maybe, Dawn, you could talk briefly about how the data is actually applied out in the world.
Yes, because one of the nice things about this project is that it's a continuation of an original project that was called the Ecological Marine Units, that was commissioned by the Group on Earth Observations to provide a global ecological characterization of the world's oceans. And the Group on Earth Observations commissioned a global ecological marine units, which is that's a chapter in volume 1 of GIS for Science. But the next step in this was to extend this to coastal areas, particularly to characterize coastal zones in terms of their ecology and to have a systematic way of doing this within GIS. And as we're seeing here in this part of the story, the idea is to be able to capture areas where biodiversity is threatened. So this is one of the case studies in terms of islands as epicenters for species extinctions that this particular work will be useful for. And in terms of birds that are in danger, fisheries, coastal fisheries, the idea of global conservation of islands, islands as small developing nations that are actually leading the way in terms of showing us how best to preserve our coastal areas. And this work is also tied to a database of island invasive species eradications that is one of the partners of this group that Roger Sayer of the USGS is leading. This includes researchers at the University of Auckland, the IUCN, and many others. And so this chapter, the way that it was laid out in terms of the beautiful photography, the beautiful maps of antiquity and of modernity, along with, as Christian was saying, the text that tells you the story of this particular project, we think is a very nice example of a very powerful scientific story. So this leads into our next chapter, Unlocking Ocean Intelligence, which is about another very large collaborative effort. This time it was led by NOAA, and specifically Lisa Wycliffe and her colleagues within NOAA Fisheries. And the idea here was to, in fact, NOAA worked with the Bureau of Ocean Energy Management to put together a system of reporting that will help researchers, but more importantly, those who are actually managing the ocean's resources and planning the ocean, not land use planning, but ocean planning. And the idea is to be able to plan the different human uses of the ocean from its surface, sea surface, all the way down to the sea floor. And this can be for energy production, for marine transportation of goods and services like shipping, even for military readiness, certainly for conservation in terms of offshore marine protected areas.
Aquaculture.
And aquaculture as well as another big one. So this chapter is about Ocean Reports, which is their automated ocean planning analysis system. And Ocean Reports also draws upon the Ecological Marine Unit's Digital Ocean that we talked about earlier. That was one of the precursors for the prior chapter. So
let me talk a little bit about this. One of the really neat things for me, because I'm not a scientist or even a trained geographer, my background is really in publishing and editing. But in working on this book and like this chapter in particular, it really gave me an opportunity to kind of take a deep dive into something that a lot of people don't really think about. It's like all this information about the ocean is being really rapidly collected right now. And this Ocean Reports project is a very ambitious project to bring all that information into a common platform, which is a GIS platform delivered online. And so when we're building the book, when we started, we thought we wanted to build something that was kind of a hybrid between Wired magazine and National Geographic from a visual sense, and also Scientific American, and kind of bringing those three concepts of publishing together into one place so that the book could be interesting to a lay audience of people who are just generally interested in the world. And like I said earlier, and how geography and geographic science are brought to bear on these problems.
So with that in mind, you see how the visuals fill up the pages in these chapters, which is very, very appealing and something that we wish that more scientists would be able to do within the pages of scientific journals. But this,
I think this might be a good point also to mention that we have a companion website for this book and the first volume, and that can be accessed at gisforscience.com. And if you go into that website and you click on the chapter heading for this particular chapter, you'll find a lot of digital resources that allow you to actually go in and explore this data from a more hands-on standpoint.
So here is gisforscience.com, the supplementary site. Christian, did you want to say a few more words about this?
Well, what this is a collection of digital resources organized by chapter that were compiled by the authors of the book. One thing that's kind of funny about publishing books about technology is that, here we are, we're describing all this great interactivity, and these are not static maps. In many cases, they're interactive maps that you can drill into and pull up additional information on. So it's really not enough just to strictly talk about it in a book. So in this particular case, we have the individual chapters. If you click on that one, the Unlocking Ocean Intelligence. See if we can get in here. And which one is it? About the Ocean Reports tool, various digital resources connected to that. And there's the Ocean Reports tool down on the second row.
The actual tool.
Yeah.
Mm-hmm.
Yeah.
Part of the supplements is the videos that show you how to get started using this tool. But in this case, I'm just starting in terms of drawing a specific area that I'm interested in to get started. And then it will allow me to draw reports from this particular area in terms of how big it is, what the depth and elevation of that area is, what populated places are part of this, what are the federal, state, and county jurisdictions, what is the protection in this particular area, and so forth. And then you can draw upon a whole series of additional information about this particular area that I've just drawn on this map. So that's how the tool starts off working.
Mm-hmm.
Anyway, I'm back to the supplementary site. So for this particular supplementary site, there are videos, there are technical reports, there are journal articles, as well as the actual tool that was the subject of this chapter.
This is the real payload of the chapter, to tell you the truth, from an educational standpoint, because you can read the chapter in a half an hour or less, and you can go in and spend hours exploring these resources on any of these chapters.
And the GISforscience.com site is free, it's open, so you could actually go to any of these supplements without reading the chapters. But the idea is to read the chapter first and then go to the supplementary information that is present. So the next chapter that we were going to talk about is the geography of ocean plastics. So we'll go a little backwards here and show you some of the supplementary information for that chapter, which includes story maps, as well as a couple of meeting posters and journal articles. But this chapter is a little different because it also includes a GitHub repo of computer code. Go ahead, Christian.
I was just going to say, this is a chapter about modeling of the ocean surface and how plastic debris moves around. We've all heard about the great Pacific garbage patch, or the Pacific gyre. Well, this chapter attempts to actually model the surface movement of water and how those plastics are carried all around the oceans, and also gets into the source of the plastics coming out from major rivers. I think there are 12 rivers projected.
Yeah, so now we're back to the actual chapter in the book.
Right. So we open this chapter with not a very pretty picture of a beach in Africa, Ghana. And, I don't think anybody has any doubt about the severity of the ocean's plastics problems. I think somewhere in the book we mentioned the statistic that 99% of all plastics ever manufactured in human history are still in existence. They don't biodegrade. It's a huge problem. We have this issue of the what's been called the Great Pacific Garbage Patch, or the Pacific Gyre. And what this chapter does is it shows how to use GIS to actually model the sources and the movement of plastics in an attempt to eventually curb them at the source. So this diagram kind of shows two of the main convergence zones where the garbage patches are found. This is a big data problem, and this is a kind of a machine learning, artificial intelligence problem that's solved or beginning to be solved from a modeling standpoint with ArcGIS Pro. Go ahead, Don.
And this is very useful from the standpoint of not only the approach and the workflow in GIS to model the journey of plastic through the ocean, but also to talk about the actual computer code. So as Christian mentioned, this is actually a machine learning chapter, and it uses algorithms from R, the R spatial statistical package, and also showcases how R and ArcGIS can be used together for this particular application. So the authors do the modeling in R, and then they give us the map of hotspots of plastic pollution using our hotspot algorithm in ArcGIS. So this chapter is a bit more intense in terms of its scientific content, the spatial statistics that's involved. So it's for a more advanced audience, but it's talking about a problem that we are all concerned about and all want to do something about and all want to know about how we can monitor it in the future as we change our personal behavior to stop putting plastic into our water systems, into our oceans, stop using plastic altogether. But in the meantime, as Christian mentioned, we've got this big problem that already exists in the ocean. And this is how you can model interactions between plastic and between the life that it's harming. So again, going back to the supplementary section of the book, that section does actually include the R code in GitHub that was used in the chapter.
And it's actually quite easy to implement, even if you don't really understand, what you're looking at. The actual mechanics of dropping this code that you would download into an ArcGIS Pro project is just about the simplest thing you could do. So we've really made some breakthroughs in the technology of integrating advanced kind of spatial modeling and R and statistical packages in the ArcGIS Pro environment.
Now I know we're getting a little bit of short on time now, but we've talked about basically how the Earth works in terms of the first study, in terms of the mapping the global islands, how we interact or how we're changing the Earth in terms of the plastic pollution that we're putting into the ocean. But a third part of how we interact with the Earth in terms of science is how we look at the Earth. And so here I wanted to focus on the monitoring disasters chapter. This was another great example of a collaboration with a federal agency, Jeremy Kirkendall and Garrett Lane of the NASA Disasters Program. And here again, the layout of this chapter is pretty stunning in terms of understanding how NASA Earth science works with all the various satellites and the sensors that are on the in space to monitor our planet from space, and focusing on the mission of the NASA Earth Science Disaster Program, which provides a mapping portal to satellite imagery of fires, such as the Australian bushfires, floods, hurricanes, and many others. So this was a pretty terrific image that we got from NASA that's in the book. Christian, would you like to talk about?
Sure. So, I think all of us are aware that there are just a huge number of satellites orbiting the Earth and capturing all kinds of data, natural light data and multispectral data and temperature data and elevation data and all kinds of things. And it's being collected 24/7, all year round, capturing all these different events and processes that are happening on Earth. It's just an overwhelming amount of data for anybody to get their head around. And what I really love about this chapter and the work that Jeremy and his team have done at NASA is they're attempting to become kind of a clearinghouse of satellite imagery that's collected by NASA and actually other agencies too. I think they get into some of the European Space Agency data and coordinating with that. But it's just really, if you go to their website, we don't have time to show it in this talk, but it's linked in the GIS for Science companion website. And you can get on there and start to kind of systematically explore data from all the different sensors that are up there. Even if you never plan to actually use the data in your own work or your own research, it's just a fascinating glimpse into kind of man's ingenuity. You know, the fact that we've been able to get all these sensors up in space and collect the data and synthesize it and organize it and make it actually very easy to use for GIS and geography people, just to download it onto their computer and look at it, or download it and analyze it in ArcGIS Pro or ArcGIS Online. So it's a very impressive attempt, I think, to really begin cataloging all of this data that's out there. And you know, the internet has just created amazing opportunities for people to get their hands on this data. It's really exciting, and I don't think people really realize how much data is out there, just like literally a click away.
Yes, really agree. And what the NASA Earth Science Disasters Program is doing is making use of the processing and even analysis of these huge data sets in the cloud as well. So you can do quite a bit of this now, even within your web browser.
Right.
So with this particular chapter, they talk, for instance, about measuring rainfall throughout North America and South America, predicting landslides through a landslide susceptibility model that can actually live in the cloud and calculate on the imagery that's in the cloud and return the result within their portal, within the various maps there. But also, if you do have the capacity to download the data, this is a workflow, a GIS workflow, that shows you how you would go about modeling the susceptibility of a region to landslides, given the 30-minute precipitation data from satellites and other types of data layers. And they have actually calculated landslide susceptibility globally in this example here. But again, the way that this is laid out is pretty stunning in terms of the large format maps.
Yeah, you just passed the fire examples. I mean, that's just a great example out here in California. Of course, we've had a terrible fire season still going. Actually, the fire's burning very close to us right now. There are ways very easily to get into ArcGIS Online and load a fire perimeter map and what's called a VIRS, VIIRS. You could probably explain what the acronym stands for, Don, but it's actually a real-time heat map. So it's quite amazing to think that you can get on to your computer and just in a few clicks, you're actually looking at very near real-time imagery of fire incidents all around the world.
And we don't have the specifics in this particular chapter, but there are other colleagues that we're working with who are modeling the impact of these fires, these coastal fires out on the ocean in terms of the not only the air quality, but the soot, the pollution that is generated by these fires settling into the upper layers of the ocean and affecting the food chain, the ecological processes in the surface part of the ocean as well. So, and this was a great example of how NASA actually collaborated with government agencies in Australia to create the first plume model in GIS of data coming from the Australian bush fires.
Right.
So one last feature of the book that we wanted to share with you is the final section of the book, which we call the Technology Showcase. And the Technology Showcase is, we think, a wonderful way to show how Esri developers, product engineers, specialists. We have many Esri staff who are scientific experts in various areas, and they have come together to create innovations that are actually serving the needs of scientists as well. So this technology showcase is actually in a flip book as well that you can get online, and the link to this flip book is in the supplementary site that we talked about before. But in this technology showcase, for instance, starting off with the Spielhaus map that we talked about before, this is a 2-page vignette by the projection geometry team that actually created the Spielhaus coordinated projected system in ArcGIS and made this innovation available to scientists such as the JCOM scientists who requested it, as well as the cartographers, including the great John Nelson, who has come up with the color schemes and other ways that you can display this map in ArcGIS Pro.
I love this map. You know, I've showed this to a lot of people, and I don't think a lot of people realize that all the water in the world's oceans are connected. It's actually, they call it Earth, planet Earth, but it's really planet Aqua. You know, there's more water than land on this place. So it's just a beautiful depiction of it. And I think it really hits home to see it like this.
Yes, so true. And I think it's this way of looking at the planet that we need now, especially as we're trying to focus on how important the ocean is for life, no matter where we live, and also how much in crisis the ocean is on this planet Aqua, this planet ocean. Another technology showcase I'm going to flip through here was work done by our spatial statistics team to look at the patterns of the harmful algal blooms off the coast of Florida, also known as the red tides. And they have had some significant red tide events recently that have really hammered their coastal economy. So this particular vignette talks about ways that you can model that and map that in ArcGIS Pro. We have a new spatial temporal series of toolboxes of tools that help you to do that. So it's a real contribution to spatial statistics, but also to the marine ecology and fisheries communities to help them to get a better handle on what's happening given the good spatial temporal data that they might have.
So I think we're out of time now. I want to thank you for giving us the opportunity to present some information about this book. I will let you know that the book will be available in hard copy and in ebook format beginning on December 1st. And also, if you go to the geography2050.org website, there will be a link there to sign up for a free copy of the book. We're going to be giving away 15 copies of the hardcover hard copy book as soon as it's available. Thank you.
Thank you, Dawn and Christian. By the way, don't forget to join us tomorrow, Thursday, for our annual Honors and Awards ceremony, where we will recognize Dr. White for her extraordinary lifetime of achievements and present her with the George Davidson Medal. On behalf of everyone at AGS, thank you to the many organizations who make this symposium and the yearly work of AGS possible. We are especially grateful to all the organizations this year for providing your support, even though we couldn't get together physically. Your recognition of the importance of continuing this multi-year strategic dialogue, be it in person or through technology, is important and necessary. Our next lightning presentation will be by Dr. Greta Brenches from the Max Planck Institute for Marine Microbiology, and will discuss her work in the South Pacific Gyre.
Hello, my name is Dr. Greta Ranches, and today I have the pleasure of giving you an insight into the South Pacific Gyre. I begin my talk with this view of the Earth, focusing on the South Pacific Gyre, to give you an appreciation of how vast it is. Oligotrophic or nutrient-poor ocean gyres represent 40% of the Earth's surface, with the South Pacific Gyre being the largest oligotrophic gyre and covering 10% of the ocean's area. It is also the most remote gyre, as its center is the furthest from any given continent. Due to its sheer size, it plays a significant role in global biogeochemical cycles, but is rarely explored due to its remoteness. It is referred to as a marine biological desert because it has some of the clearest waters ever reported, near undetectable surface nitrate concentrations, which are essential for life, and the lowest sea surface chlorophyll A concentrations, which are a proxy for plankton biomass and primary production. The results and insights I'm giving you today were produced during one of the few scientific expeditions into the South Pacific Gyre, the SO245 Ultraback expedition. Our goal was to investigate the biogeochemical, microbiological, and ecological processes in the South Pacific Gyre. We traveled across the South Pacific Gyre on the research vessel Zonner with 33 scientists. During our expedition, we sampled the water column from 20 to 5,000 meters depth over a geographic distance of 7,000 kilometers, and also took samples from the seafloor. We measured the physiochemical conditions of the environment and analyzed the microbial community, as they are the primary drivers responsible for biogeochemical cycles in the marine environment. The South Pacific Gyre is characterized by pronounced changes in physiochemical conditions in the upper 500 meters, as shown by the contour plot and of temperature and fluorescence with depth on the left. Comparatively, the deeper waters, the plot on the right, the conditions are relatively consistent. In the central gyre, marked here by the arrow, the water temperature peaked at 25 degrees at the surface, with virtually no chlorophyll A measurable in the surface waters down to 70 meters. However, at 190 to 20 meters depth, there was a pronounced DCM, which is a deep chlorophyll maximum. This was exceptionally low and is interesting because it indicates that although the surface waters are too nutrient limited or too high in solar radiation for primary production can occur in lower or deeper waters. Now, the South Pacific Gyre has some of the lowest surface water cell abundances ever recorded. But at the deeper depths, about 100 meters, the cellular abundance increased and maximized just above the DCM. This highlights that although the surface waters are a desert, there are organisms present at deeper depths. Now, during our expedition, we identified the microorganisms throughout the water column for the first time and found that surface waters were dominated by specialist oligotrophic organisms. Between 100 to 200 meters, there were primary producers such as cyanobacteria, corresponding to the depth of the DCM. And in deeper waters, there were specialist deep oligotrophic organisms. We found many bacterial groups which are known oligotrophic specialists. However, I'd like to highlight one interesting finding from our expedition. One organism, the Aegean 169 group, showed particularly high relative abundance in the ultra-oligotrophic top 20 meters of the gyre. Is it adapted to the survival of this low nutrient, high solar radiation environment? The research is still ongoing. In addition to investigating the water column microorganisms, we also took samples from the sediment of the South Pacific Gyre. To analyze the subsurface microorganisms, here an example of the South Pacific oxic deep sea sediment with the occasional manganese nodules on the surface. Now, due to the extreme low flux of carbon from the surface of the South Pacific Gyre, the sediment is millions of years old. Additionally, the sediment is oxic due to extremely low net activity or respiration rates. This is very unusual, as normal marine sediments are anoxic due to high microbial respiration. This ancient oxic and seldomly researched sediment could hold unique ancient microbial life. To conclude, the oligotrophic gyres cover vast areas of the Earth's surface and are important in global biogeochemical cycles. The South Pacific Gyre is the largest oceanic gyre and, in part due to its remote location, has only received limited scientific investigation. However, our analysis of the microbial community of the surface waters of the South Pacific Gyre have shown that although it is oligotrophic, primary production occurs throughout a deep euphotic zone. These findings indicate that although the South Pacific Gyre appears as a marine biological desert from satellite imaging, it may impact global biogeochemical cycles more than previously believed and calculated. And with that, I would like to thank you for your attention, thank the American Geographical Society for the opportunity to present these insights into the South Pacific Gyre. I'd also like to thank the scientists and collaborators of the UltraPAC expedition. And I'd like to thank the funding agency, the Max Planck Society, and the German Federal Ministry of Education and Research for funding this research.
Thank you, Dr. Rentjes. And quickly moving to the next lightning, welcome to Ms. Carol Lockhart, who is the Chief Hydrographer at Wolpert, who will be discussing bathy LiDAR object detection. Ms. Lockhart?
Hi, my name's Carol Lockhart and I'm with Wolpert, and I'm going to talk to you today about bathy LiDAR object detection and what's possible with the latest generation sensors. In 2018, we used a Chiroptera 4X sensor to conduct a high-resolution topobathy LiDAR survey to increase the navigational safety of Tonga and Niue. The survey was conducted as part of the IXBLUE team for Land Information New Zealand, who in turn were doing this as part of the Pacific Regional Navigation Initiative. The goal of the PRNI is to allow safe and reliable passage through Pacific waters, while protecting fragile ocean environments and allowing Pacific Island countries' economies to develop. The project used a combined sensor approach, with EOMAP providing satellite-derived bathymetry first, followed by Wolpert providing airborne LiDAR, and then IXBLUE performing a multibeam survey. Overall, everyone involved found this to be a really great approach, with lots of benefits that could be discussed at length in a separate discussion. Today, I'm going to focus on some analyses we were able to conduct because we had such a large overlap between the LiDAR and multibeam. The LiDAR was acquired 4 to 5 months ahead of the multibeam and was planned to achieve hydrographic object detection to 20 meters depth, with multibeam performing object detection deeper than that. But the LiDAR was acquired to extinction in most locations, and the multibeam data came in shallower where it was safe to do so. This resulted in over 50 square kilometers of overlap, covering depth ranges from 5 meters to 45 meters. Since the LiDAR can survey shallow water more efficiently than the multibeam, we wanted to assess how reliable the LiDAR object detection was with a modern sensor. When conducting the object analysis, in the past this has been done by examining specific objects at the point cloud level. But this gives us tunnel vision almost immediately and can lead to us focusing on differences that don't really matter to the final product. It's also very difficult to scale this approach to large areas. Therefore, we wanted to do the analysis on the chart product or a proxy for that product, since at the end of the day, it's those differences that really matter to the mariner. For the analyses, we used a proxy for the largest production chart scale. We then used focal statistics to interrogate the LiDAR and multibeam final bathymetric surfaces, taking into account that largest chart scale. This process identified where the chart would end up being different between the two technologies. Once we had our difference locations, the first thing we did was assess them to see if there was any depth correlation, but we didn't find any. Likewise, we were curious if environment type made a difference. Again, we didn't find any strong correlation. Across the overlap area, we found 71 grid cells where multibeam identified something, where LiDAR had no correlating object. We also found 76 grid cells where the LiDAR identified something and multibeam had no correlating object. However, over 12.5 million grid cells agreed. In other words, we achieved 99.999% matching in the overlap areas. Let's look at more closely at a few representative examples in the point clouds. Here, the multibeam in red clearly detects the object. If we look only at the LiDAR data for the same location, we see that the LiDAR detected the object, but the data on top of the object is flagged as rejected. This is an editing error. We also saw examples of this in reverse where multibeam was flagged as rejected. In this example, it appears that the object is represented correctly, both by the multibeam and LiDAR point clouds. However, if we look at the multibeam surface, it isn't pulled up to the shoal as sounding. This was the most common error we saw and highlights the importance of knowing the largest scale for which the surface will be used, since the surface is what's passed on for charting purposes. There are techniques we can use to highlight these potential issues at a given scale before finalizing the surface for delivery, but the scale has to be known. During the editing phase for this project, the final product scale hadn't been decided by LINS. This was their first time using this approach, and they wanted to understand what they could achieve first, which is understandable. On future surveys, I would expect this to be less of an issue, and therefore it would drastically reduce the number of surface representation issues. So in conclusion, we need to make a distinction between object detection and object recognition. In most cases, the sensors detected the objects, but they weren't always recognized during editing as such. There were editing mistakes in both LiDAR and multibeam because there's still a human factor present in processing of these complex data sets. As discussed already, scale matters. I like to think of map once, used many times as really being survey once, map many times. Once we have the raw data, we can process and classify it very differently depending on the required project scale and purpose, with potentially very different levels of effort required. To that end, although not discussed here, seabed reflectance data, orthorectified image mosaics, and topo LiDAR were collected simultaneously with the Bathy LiDAR, and all of this data was processed and delivered for multi-purpose use by the local stakeholders, not just for updating of the nautical charts. I think it's important to remember that the analysis showed the success rate here was very high, and likely would be higher if product scale had been available during processing, as it would have reduced many of the surface representation issues which caused the majority of the differences we saw. And lastly, the combined project approach was very successful to help achieve the goals of PRNI. If we use the right tool at the right time, in the right location, we can survey more efficiently and effectively. And this analysis showed us that the LiDAR was the right tool to provide efficient high-resolution surveys in these types of environments. Thank you for your time. I really appreciate it. I hope you found this interesting.
Thank you, Ms. Lockhart. And now we have a spotlight session with Jamie McMichael, the director of Seabed 2030, whose mission is to map the entirety of the seafloor within the next decade.
I'm Jamie McMichael Phillips. I'm the director of the Nippon Foundation JEBCO Seabed 2030 project. I'm absolutely delighted to have been invited to participate in Geography 2050, the future of the world ocean. I'm also speaking today as part of the Exploring, Mapping and Sensing the Ocean session. I know that you may have already heard about Seabed 2030 from other speakers, and indeed you may hear even more later on as the whole series of sessions progress. But just an introduction to Seabed 2030, what it is, what we're aiming to achieve, why we're doing it. I will say a few words, but crucially, we have a movie to play after I've spoken, which will set the context and allow you to learn more about Seabed 2030. But just to set that scene, Seabed 2030, the full name is the Nippon Foundation JEBCO Seabed 2030 project. It is a collaborative project between the Nippon Foundation and the General Bathymetric Chart of the Ocean project, JEBCO by any other words, to map the world's ocean floor by the year 2030. We all know, and I know I'm talking to experts here, that the ocean floor shape influences a whole host of Earth's processes. And the ocean floor shape is key in addressing a range of global safety, security, health issues, including climate change, sea level rise, tsunami wave propagation. Not to mention biodiversity and, of course, safety of navigation. All rely on a knowledge of the shape of the ocean floor. The oceans cover almost 3/4 of the Earth's surface, yet today we know surprisingly little about the shape of the ocean floor, with about 85% of the ocean floor yet to be fully explored. Seabed 2030 aims to bring together organizations and individuals to take part in helping us to gather data to form that ocean map and to be able to deliver it by the year 2030, to make it freely available to anybody who wants to use it, be you an individual or be you an organization. So without further ado, thank you for inviting me to participate, and over to the movie.
Mapping the ocean is undoubtedly the last great frontier of exploration on planet Earth. We know more about Mars, we know more about our moon, we know more about Jupiter than we do about our own oceans. The shape of the seabed is fundamental to ocean current circulation, how we predict sea level rise, how we predict the path of tsunamis, and we need that seabed map to provide base level data for something that's a life-changing project, something that will affect climate prediction, sea level rise, and the stewardship of the oceans. Now is the time that we actually need to set a deadline. 2030 is a deadline to achieve 100% mapping of the seabed. We need to have that deadline to give us something to aim for. This is an absolutely revolutionary and ambitious project. The organizations behind it are the Nippon Foundation of Japan and the JEBCO community. So we had a team from around the world of Nippon alumni who worked together night and day for about 3.5 years to build an underwater autonomous vehicle carrying a sonar system with an unmanned mothership that went out and surveyed the ocean floor. They can go to sea for far longer than traditionally manned vessels, and they can operate 24/7 around the globe. The carbon footprint is reduced because they're not carrying such heavy payloads, and they can achieve what we need much more quickly. It is the way that the maritime industry is moving, and it's the way we need to move if we're going to achieve our aims. We send a ping from the sonar system down to the bottom of the seabed, and we listen out to hear the ping come back, and we measure the time difference. With a modern multi-beam system, we send many more pings out to get a really high resolution, wide angle picture of the seabed. We can use that to deliver what we need to complete our seabed mapping by 2030. We need the backing of governments, we need the backing of industry, we need to be able to mobilize the world's surveying platforms, manned and unmanned, to go out there and gather the data. And we also need the public to spread the word that this is a project for the benefit of all mankind. We have one jigsaw piece at the moment, 19% of the ocean floor mapped. We need to fill in the other pieces. So join us on this great discovery that will benefit humanity.
Thank you, Jamie. That was really great. You've probably heard the expression, the Internet of Things. Well, today we have Mr. Mike Botts, who is going to take us through the ocean of things. Mike is the president and founder of Botts Innovative Research, and we are eager to hear his story. Mike?
Hi, I'm Mike Botts. I've been involved in developing open sensor standards for quite some time and in implementing these standards within various communities such as the oceans community. Today I'd like to talk about the past, current, and future use of sensors within the ocean community. Since man began navigating the seas, he's been concerned about ocean measurements, mostly about location, direction, ocean depth, weather, and weather forecast. But other observations such as temperature, ocean geology, biological samples, water chemistry, and such have also been important. Man's experience with buoys first started off as providing alerts, warning when you're too close to the coastline or perhaps when the waves are too choppy. But they have evolved tremendously over the last so many years in the ability to communicate through satellites and provide all sorts of measurements. Because of the challenges involved in getting measurements off of free-floating buoys, most of the early ocean measurements utilized moored systems. Underwater cables were provided for power and for a path of observation. With these moored systems, that greatly increased the diversity of measurement types. And then came floats, which were able to communicate through satellite systems to report their measurements. And what that resulted in was a more densely sampled ocean than we had previously had. As we get to where we're building more inexpensive floats and providing those out into the ocean, that will even increase more. There are also gliders that basically get set on a path, and as they go along that path, they will descend and ascend in the ocean to provide measurements that are depth dependent. Now, we also have what are called UUVs and AUVs, unmanned underwater vehicles and autonomous underwater vehicles. These, like UAVs, will go under the ocean and take measurements either in situ, or in some cases they will have sensors such as LiDAR that allow us to map the seafloor. And some of these can be quite large, as you can see, if you compare them with the silhouette of the man in that image. And then finally, sometimes we want to do more than just observe. We want to be able to do things under the ocean. So then we have what you might call robots. Now, we talked about satellites are important for communicating with floats, but they are also providing us a platform for being able to take measurements, sea surface temperature, wave heights, or whatever, from space. This allows us to fill in a lot of the gaps that currently exist in the buoyed systems and such. Now, we also still use airplanes like on Earth or UAVs in many cases. These can do things like measure the bathymetry, the ecosystem, detect a groundwater discharge under the ocean, and monitor animal behavior, as well as actually allow us to map the litter that we're finding in the ocean. Now, the animal trackers, it's important that they do more than just let us know where the animals go. They need to know, we need to understand why they go there, what environmental stresses they are experiencing, and are they changing their behavior due to these stresses. We need to combine tracking with other observations to make these kind of measurements. And also, there are autonomous ships. These are USVs, or unmanned surface vehicles. Some of them can be driven remotely. Some of them drive themselves. Some of them are powered by motors, and some are cell systems, similar to the one on the left. So now, what happens when all of these sensors are connected? We start to look at what some people might call the ocean of things. And like the Internet of Things, where tons of smart devices can be sprinkled all across the ocean, and these can become networked and connected. This allows us to start to utilize different measurements within different systems to be able to visualize or process various data.
Now, it's not enough that these devices can communicate home or even communicate with each other. The ocean will become crowded with these devices, whether we call them things, sensors, or robots. And they will only be able to successfully work together to make sense of the ocean if they participate in a common 4D framework and speak a common language. Once all of these sensors, things, and robots can understand each other's observations across space and time, we believe they will be deserving of the name georobots. So it's critical that these systems be able to be geographically aware, discoverable, to be able to support processing on the cloud or on the edge, and be supported by a framework to bring all of this together. And that framework should be based on open standards, open APIs. Open Sensor Hub is one such a framework. Thank you.
Thank you, Mike. And that wraps up today. We hope you enjoyed the program. Be sure to stay tuned Thursday when we look at the bounty of the oceans and protecting our blue planet. For now, goodbye and see you tomorrow.